They lied to us about the Big Bang. Everything you think you know about how the universe began is probably wrong. Imagine a moment where there's absolutely nothing. No stars, no planets, no light, no time, just an endless void of nothingness. And then out of nowhere, everything explodes into existence. Space stretches, time begins ticking, and a universe bursts forth so violently and so perfectly that it gives rise to galaxies, stars, and eventually us. But here's the thing, nobody truly knows how it happened. Scientists have theories. Wild ones, mind you. Some believe the universe started from a speck smaller than an atom and then inflated faster than the speed of light. Others think it might have emerged from a collision of higher dimensions, like two cosmic brains smashing into each other. Then there's the idea that this isn't even the first universe. What if everything we know is just one cycle in an endless loop of expanding and collapsing universes? What if there was no beginning at all? The deeper we dig into this mystery, the stranger it becomes. How does something come from nothing? Is nothing even real, or is it just something we don't yet understand? And here's the kicker. What if the universe isn't the only one? Could there be countless other universes out there, each with its own laws of physics, its own stars, and maybe even its own version of us? Every theory raises more questions than answers, and the truth might be more mind-bending than anything we've imagined. So what really happened in that first unimaginable moment? To unravel the mystery of the universe's beginning, we need to challenge everything we think we know. Curious? You should be. Let's dive into the strangest story ever told. 13.8 billion years ago, the greatest mystery in the history of existence unfolded. The universe began. In a fraction of a second, everything we know, space, time, matter, and energy, burst into existence from what seems to be nothing. But how? How can something as vast and complex as the universe emerge from absolute nothingness? This isn't just a question for science, it's a question for anyone who's ever wondered about their place in the cosmos. The story of the universe's birth is a puzzle we've been trying to solve for centuries. And even with our most advanced tools and brilliant minds, we're left grappling with theories that are as fascinating as they are incomplete. Take the Big Bang, for example. Most people think of it as an explosion, a chaotic event that scattered matter across a void. But that's not quite right. The Big Bang wasn't an explosion in space. It was the sudden expansion of space itself. Before it, there was no space, no time, just an infinitely dense and tiny point scientists call a singularity. At least that's one theory. But this explanation raises even more questions. What caused the singularity to expand? What existed before it? And perhaps the most perplexing question of all, is there even such a thing as before? For decades, scientists have tried to answer these questions, blending the realms of physics, philosophy, and mathematics, from the mysterious Planck era, a time so short and so strange that even our most advanced theories can't describe it, to the rapid inflation of the universe. Every step in this cosmic story is filled with awe-inspiring discoveries and head-scratching enigmas. And yet, there's still so much we don't know. Some theories suggest that our universe is just one bubble in a vast multiverse, where countless other universes expand and contract in an endless cosmic cycle. Others propose that the universe emerged from a collision of higher dimensional spaces, creating a spark that ignited everything we see around us. But here's where it gets even more fascinating. Every theory we have, every model we build, forces us to confront something deeper. The limits of human understanding. What does it mean to say the universe began? Can something truly come from nothing? And if the universe had a beginning, does that mean it will also have an end? These aren't just abstract ideas for scientists to argue about in laboratories. They're the questions that define our existence. Every star in the night sky, every atom in your body, every thought you've ever had, it all traces back to that mysterious beginning. And if we can understand how the universe started, maybe we can understand why we're here at all. So buckle up. This isn't just a story about science, it's a story about us, about everything, and about the greatest mystery of all. How did the universe begin? Picture this, 13.8 billion years ago, there was nothing. No stars, no galaxies, no planets, not even the empty space we see today. And then in an instant, boom, there was everything. Space, time, energy, matter, everything you see around you, including yourself, came from a point of unimaginable density. This event, known as the Big Bang, is often depicted as an explosion. But here's the twist. It wasn't an explosion in space. It was the creation of space itself. And that's just the first problem we face. The Big Bang didn't happen in some pre-existing space. It was the very birth of space. Imagine trying to comprehend something that literally has no context, like trying to understand how you can be alive when there's no time yet. Space didn't exist before the Big Bang, so how can we even talk about what came before it? Our concept of time is wrapped up in the idea of progression, before, during, and after. But before the Big Bang, there wasn't any before. This brings us to our first mystery. What came before the Big Bang? Some scientists suggest that time itself started with the Big Bang, and anything that could have happened before it is just meaningless. Others, however, argue that there might have been a pre-Big Bang universe, maybe a multiverse where countless other universes have come and gone, or perhaps a series of expanding and contracting big bounces rather than a one-time explosion. Then there's the second problem that comes up with the Big Bang: the uniformity of the universe. How did everything become so evenly spread out, especially when some parts of the universe are so far away, we can't even see them? The Big Bang theory can't explain how the temperature and structure of the universe ended up so similar everywhere. That's where the theory of inflation comes in. It suggests that, for a fraction of a second, the universe expanded at an incomprehensible rate, doubling in size many times over. This rapid expansion smoothed out the temperature and distribution of matter. But again, this only leads to more questions. What caused inflation to begin? And why did it stop? Here's another head-scratcher. The laws of physics we use today, including gravity and quantum mechanics, don't work together at the tiny scales of the early universe. Gravity, as we know it, is described by Einstein's theory of general relativity, which works perfectly for large-scale structures like planets and galaxies. But on a quantum scale, where particles are smaller than atoms, quantum mechanics rules. The problem? These two theories don't play nicely with each other. At the beginning of the universe, they had to work together, but we still can't explain how. This leads to the final big question. Can we ever find a theory that unites quantum mechanics and gravity, one that explains everything about the universe's birth? As you can see, the problem isn't just that we don't know how the universe began, it's that everything we've discovered so far raises more questions than answers. The true story of how the universe came to be is more complicated and more bizarre than we could have ever imagined. Let's dive deeper into what we know and what we still don't understand. The beginning of time. To grasp how the universe began, we need to go back to a time, well, not even a time really, because before the universe began there was no time. Sounds bizarre, right? But that's the key to understanding the most mind-boggling question in all of science. How did everything begin? Let's imagine for a moment the concept of nothing, a universe without stars, planets, space, or even time. Can you picture that? It's nearly impossible because everything we know about reality is based on the existence of time and space. But in the very beginning, 13.8 billion years ago, there was a moment, before there was anything, that defies human understanding. A moment where time itself didn't exist. A place where there was no space, no stars, no galaxies, and no laws of physics. Scientists call this initial state the Planck era, the most ancient moment in the history of the universe. It's named after Max Planck, the theoretical physicist who first proposed the fundamental scale of measurement for space and time. And here's where things get weird. The Planck era lasted a fraction of a fraction of a fraction of a second, less than a trillionth of a second. And during this infinitesimal blink in time, the universe, which was once as tiny as the size of an atom, existed in a state of complete chaos and instability. Now, let's take a deeper dive into this and see why the Planck era is such a crucial piece of the cosmic puzzle. Before the universe began, there was absolutely nothing, not even a vacuum. This isn't nothing in the way we think of emptiness today. In the absence of space, time was also absent. You couldn't measure time because it had no beginning. In fact, the concept of beginning doesn't even apply here. To really get your head around this, Let's try and imagine how strange and mind-bending this truly is. Our entire understanding of existence is based on the idea that time flows forward, a before and an after, a past and a future. But in the Planck era, none of that existed. No events were happening because there was no time for events to happen. Space didn't exist either. Nothing had form or substance. All that we think of as reality, every single thing in the universe, simply wasn't there. This doesn't just break our understanding of physics, it shatters it completely. It challenges everything we've learned about the rules of nature. And this is where physics starts to encounter a barrier. The universe, in this time before time, behaves in ways that simply don't fit into our current understanding. In the Planck era, the rules governing our universe were completely different from anything we can observe today. This is a place where quantum mechanics, the science of the very small, takes center stage. In our everyday experience, we deal with large objects, planets, cars, or even atoms. The forces that govern these things are relatively easy to understand, at least in broad terms. This is where general relativity comes in. Developed by Albert Einstein in the early 20th century, general relativity explains how massive objects, like planets, stars, and galaxies, warp the fabric of space and time, creating gravity. If you think of space-time as a stretched-out rubber sheet, planets would be like bowling balls that create a dent in the sheet. Now, you might think, well, gravity and quantum mechanics seem pretty straightforward, right? The problem arises when we attempt to reconcile these two theories. General relativity works incredibly well when we're dealing with large objects, but when you shrink down to the microscopic world, it doesn't work as well. Quantum mechanics, which governs the behavior of subatomic particles, tells us that at the very smallest scales, things don't behave in the predictable ways that general relativity suggests. Instead, particles exist in a state of probability and uncertainty, as dictated by the Heisenberg uncertainty principle. This means that at the smallest scales, there is no absolute certainty about where particles are or how they behave. In the Planck era, both forces were trying to operate at the same time, creating a situation that's currently beyond our comprehension. We don't have a theory that can describe the behaviors of gravity and quantum mechanics simultaneously, and this is one of the greatest mysteries in modern physics. But eventually, something extraordinary happened. As the universe began its expansion from the Planck era, it was not just the matter that started to take form, it was the very fabric of space-time itself. Space-time, as we understand it, is the stage on which the play of the universe unfolds. But in the Planck era, space and time weren't separate. They were intrinsically tied together in a way we can hardly grasp. The moment the universe started to expand, space itself stretched, and with it, time began. But again, it wasn't time in the way we experience it. There was no clock ticking. There was just the beginning of what we now call time, a process that began alongside the birth of the universe itself. At this point, space was not empty in any traditional sense. It was filled with an incredibly hot, dense soup of particles and energy, existing in a state of quantum uncertainty. And it's from this chaos, this quantum foam, that the universe would eventually grow into the vast expanse we see today. One of the more surreal aspects of the Planck era is the quantum foam. This term was coined by John Wheeler, a physicist who helped shape modern quantum theory. At incredibly small scales, far smaller than atoms, space itself isn't smooth and continuous. Instead, it's jittery and unstable, as if space were bubbling or frothing like a pot of water boiling. Imagine you're looking at space through a microscope, but this isn't just any microscope. This one can zoom in all the way to the Planck length, about 1.6 by 10 square is 35 meters, far smaller than anything we can measure. At this scale, space itself is in constant flux, with tiny fluctuations occurring everywhere. In a way, these fluctuations represent the birth of particles and energy out of nothing, but nothing is truly nothing. Instead, these fluctuations in quantum foam are the ground state of all matter and energy. The process is mind-boggling. Pairs of particles, like electron-positron pairs, would spontaneously form and annihilate each other in an instant, leaving no trace. The energy for this comes from the quantum fields that permeate all space. It's like an invisible sea of energy, constantly bubbling into existence and then vanishing in the blink of an eye. This quantum foam could hold the key to understanding the earliest moments of the universe and even the nature of dark energy and dark matter. The Planck era didn't last long, less than a trillionth of a second. But during that brief, unstable moment, the universe was at its most energetic. It was an era defined by cosmic chaos. Matter, energy, and time were all in a state of constant flux, with the laws of physics we understand today not yet formed. Think of this period as the universe's wild adolescence, unstable, explosive, and barely holding together. But the universe didn't stay in this chaotic state for long. Eventually, the universe began to expand at an incredible rate, a period known as inflation. And with this expansion came the separation of forces. The forces we recognize today, like gravity and electromagnetism, began to split apart from one another, like ice cubes melting in the sun. This process would set the stage for the universe as we know it. The universe began to cool, and matter started to coalesce into the first particles, quarks, electrons, and other fundamental building blocks. The Planck era is the ultimate enigma of our universe's birth. It's a time before time itself, an era in which the laws of physics break down, and the very fabric of reality, space, time, and energy, was being born. It's one of the least understood periods of the universe, but it's the most important for understanding everything that came after it. So when you look up at the stars and wonder how it all began, you're really asking about something that defies comprehension, an era where the universe didn't exist in the way we understand it today. And yet it set in motion everything that followed: the galaxies, the stars, the planets, and even life itself. It was a beginning not just of everything we know, but also of everything we still don't understand. The question remains, how did all of this come from nothing? The answer may be out there, waiting for us to discover it. If only we can unlock the secrets of the Planck era. Inflation, the universe's growth spurt. The Big Bang Theory has been the bedrock of our understanding of the universe's origin for decades, but it doesn't explain everything. One of the most puzzling issues with the Big Bang Theory was the uniformity of the universe. Why does the cosmos look so homogeneous? Why does the temperature across vast distances remain remarkably the same despite the fact that different regions of the universe are so far apart that light hasn't had enough time to travel between them? This led to a major problem known as the horizon problem. It was in the 1980s that physicist Alan Guth proposed a groundbreaking idea that would solve this issue and change the way we understood the early universe. This idea became known as cosmic inflation. To understand why inflation is such a vital piece of the puzzle, we need to take a deeper dive into the moment just after the Big Bang and explore why the universe expanded so rapidly in such a short period of time. Before inflation, a universe in chaos. Before inflation, the universe was an unimaginable place, chaotic, dense, and extremely hot. This was the time just after the Big Bang, when the universe was in its earliest moments, where space, time, and even the fundamental laws of physics were in their infancy. Understanding this state of the universe is difficult because it's so far beyond our everyday experience, and we don't have direct observations of this period. What we do know, however, comes from both theoretical predictions and indirect evidence gathered over the decades by scientists trying to piece together this primordial chaos. Imagine a point where the entire universe existed in a state smaller than a single atom. It wasn't just a small, dense point of matter. It was also packed with energy, radiation, and the fundamental forces of nature compressed into a tiny, almost inconceivable space. The temperature of the universe during this period was so high that matter couldn't even exist as we understand it today. Instead, it was in a state of pure energy, with particles constantly being created and annihilated in an ongoing, violent process. This environment was like a furnace, an incredibly dense, incredibly hot soup of particles and energy that formed the foundation for everything to come. At this time, there was no concept of space as we know it. Space itself was not yet stretched or expanded. Space and time were not yet distinct concepts, but rather were tied together in a unified fabric known as space-time. It was only as the universe began to cool down and expand that space and time began to take shape as separate entities. But in those first fractions of a second, everything was in a single, unified state, and the universe was a chaotic, energetic entity in which every corner was filled with fluctuations of energy that were far beyond our ability to comprehend. The conditions during this early period were governed by the extreme nature of the universe's density and temperature. The temperature of the universe was estimated to be so high, billions of degrees, that the basic building blocks of matter, such as quarks, leptons, and electrons, could not form. Instead, the universe was dominated by radiation in the form of high-energy photons. These photons were in constant interaction with the fundamental particles that were still emerging from the vacuum of energy. In this state, the forces of nature that we take for granted, gravity, electromagnetism, and the strong and weak nuclear forces, were all unified into a single force. This unified force was unlike anything we experience today. At such extreme conditions, the four fundamental forces of physics that govern our universe were intertwined, making it impossible to separate them. Gravity, electromagnetism, the weak nuclear force, and the strong nuclear force were all part of a single, powerful force that was shaping the early moments of the universe. The force that would eventually cause the expansion of the universe and the separation of these forces into their current forms was not yet in action. The forces were simply one entity, all acting together in a way that is beyond our current ability to model accurately. As the universe continued to evolve, energy levels were so high that particles behaved in ways that defy our usual understanding of physics. Every type of particle you can think of was constantly being created and destroyed in an ongoing process that left no permanent matter behind. Quarks, fundamental particles that make up protons and neutrons, flitted in and out of existence, and electrons and positrons, the antimatter counterparts of electrons, were constantly annihilating one another in bursts of energy. The universe was like a storm of energy and particles constantly crashing together and being destroyed in the blink of an eye. But even within this apparent chaos, there were underlying principles that began to govern the universe's behavior. Quantum mechanics, which governs the behavior of very small particles, started to emerge as the primary framework for understanding how the universe functioned on microscopic scales. Quantum fluctuations, tiny random variations in energy, were present everywhere in this early universe. These fluctuations, which are the building blocks of quantum mechanics, played a crucial role in the eventual formation of structures in the universe. Although the fluctuations were incredibly small, they held the seeds of everything that would come later: galaxies, stars, and all the matter we see today. As the universe expanded, it cooled. As it cooled, the energy condensed into the particles that would later form atoms. The formation of particles was the first step in creating the matter we know today. But before matter could take on any recognizable form, the universe had to go through a process where energy converted into particles and radiation in a state of high density and high energy. It was during this phase that the laws of physics, as we understand them, began to emerge from the chaos. The universe was also not yet homogeneous. Early on, it was filled with random fluctuations of energy, but it wasn't evenly distributed. Matter wasn't just a smooth, featureless fog. It was lumpy, clumpy, and dense in some places, with less dense regions elsewhere. The fluctuations were tiny, but they were crucial because they set the stage for the formation of galaxies and stars billions of years later. These initial differences, these quantum fluctuations, were stretched and magnified as the universe expanded, creating the large-scale structure we see in the cosmos today. It was as if the seeds of galaxies were already sown, waiting for the right conditions to grow into the vast networks of galaxies that we see today. This is where things get even more interesting. In the very early universe, these quantum fluctuations weren't just random. They were a critical part of how the universe would evolve. As the universe expanded and cooled, these tiny fluctuations in energy began to stretch and grow larger. The process that caused this was inflation, an incredibly rapid expansion of space itself that occurred in the first fraction of a second after the Big Bang. This rapid expansion stretched out the initial variations in energy, setting the foundation for the large-scale structure of the universe. Before inflation took place, the universe was like a chaotic stew of matter, radiation, and fluctuating energies. But after inflation, the universe became something much more ordered, with a vast, uniform distribution of energy that laid the groundwork for everything we know today. The initial quantum fluctuations, which were microscopic, became the seeds of galaxies and other structures in the universe. In this chaotic early universe, the processes that we take for granted today, gravity, the creation of particles, the formation of atoms, the cooling and expansion of space, were still in their infancy. There was no matter as we understand it today, just particles and energy constantly interacting. It was only as the universe expanded, cooled, and evolved that the forces that govern everything we experience began to settle into their familiar forms. Even with all this chaos, the early universe was laying the foundation for everything to come. It was a time of unimaginable energy and violent interactions, a time when space itself was being born. Every single step in this chaotic process set the stage for the eventual formation of the universe we now see around us. The matter that would form stars, planets, and galaxies was being created in tiny, imperceptible steps. What began as a violent, energetic burst would eventually lead to the calm expanses of space and time we now experience, with galaxies and stars shining brightly in the dark. The story of the universe before inflation is one of utter chaos and incredible complexity. It's a time that challenges our understanding of reality and reveals just how little we truly know about the beginning of everything. And yet, despite all the chaos and confusion, there were moments of clarity. Tiny fluctuations in energy, small seeds of matter, were already shaping the destiny of the cosmos. These fluctuations would eventually give birth to the galaxies, stars, and planets that would make up our universe. Before inflation, the universe was an energetic, chaotic place. After inflation, everything changed. From that point on, the universe would never be the same again. It would begin to cool and settle into a more recognizable form, one where the forces we are familiar with today began to take shape. But that's a story for another time. For now, what's important to understand is that the chaotic, high-energy universe before inflation was the crucible from which everything we know today was forged. It was an essential part of the puzzle, a time of incredible upheaval, and it set the stage for the universe as we see it now. The mysteries of the early universe are just beginning to unfold, and with each new discovery, we are uncovering more about the origins of everything that exists. What is cosmic inflation? Cosmic inflation is one of the most revolutionary ideas in modern cosmology, and understanding it takes us to the very heart of what we know and what we don't about the universe's origins. At the core, cosmic inflation is a theory that proposes the universe underwent a mind-bogglingly rapid expansion in the first moments after the Big Bang. This expansion was so fast, so violent, that the universe grew exponentially in less than a trillionth of a second. To grasp the full impact of inflation, we need to rewind to a time just after the Big Bang, when the universe was not only unfathomably small, but also incredibly dense. In those early moments, the universe was a hot, chaotic sea of particles, energy, and radiation, all packed into a tiny space. Think of the universe as an incredibly hot and dense ball of fire, but in a form far beyond anything we can easily comprehend. Everything was compressed into an infinitesimally small point, a singularity, where the laws of physics as we know them simply break down. There were no stars, no galaxies, and no space or time as we understand it. It was the absolute beginning of everything. Yet it was also beyond our current ability to describe fully with the laws of physics we know today. Despite this chaotic environment, something extraordinary happened. In a fraction of a second, the universe expanded at an incredibly fast rate. At this point, all the energy, all the particles that were trapped in this tiny space began to stretch and rapidly grow outward. The concept of cosmic inflation explains how this rapid exponential expansion of space allowed the universe to expand from an almost unimaginably small point to a vast, observable universe in a fraction of a second. This period of inflation was so quick that the universe expanded by a factor of at least 10^26 times in less than a billionth of a second. To give you a sense of how massive this expansion was, imagine a balloon that starts at the size of a grain of sand and grows to the size of the Earth in the blink of an eye. That's how rapidly space itself inflated during the first few moments of the universe's existence. The idea of inflation was proposed by physicist Alan Guth in 1980 as a solution to several problems that had stumped scientists for years. Before inflation, the Big Bang theory suggested that the universe began from a hot, dense state and then expanded, cooling as it did. This model could explain many things, like the abundance of light elements like hydrogen and helium in the universe, and the cosmic microwave background radiation. But it couldn't account for some key observations that puzzled cosmologists, such as the uniformity of the universe. The universe as we observe it today is smooth. No matter where you look, whether toward the edges of the observable universe or deep into the heart of our galaxy, the temperature is almost the same. When we measure the temperature of the universe's background radiation, we find that it's remarkably uniform, with a temperature of about 2.7 Kelvin, just a few degrees above absolute zero. This is strange because in a universe where light can only travel so fast, distant parts of the universe shouldn't be able to communicate with each other. If the universe began as a hot, dense ball and then expanded, how could distant regions of the universe have the same temperature and similar properties if they hadn't had enough time to exchange information? This problem became known as the horizon problem, and it was one of the key reasons the idea of inflation became so popular. Inflation solves this problem by suggesting that, in the very early universe, space expanded so rapidly that distant regions of space were once much closer to each other. During this rapid expansion, regions that we now observe as being vastly separated were once in contact, allowing them to exchange information and reach thermal equilibrium. After this brief moment of rapid inflation, the universe expanded more slowly, and these regions were pushed so far apart that light could no longer travel between them. But because they had been in contact before inflation, they remained in thermal equilibrium, which is why the universe appears so uniform. But the horizon problem wasn't the only issue that inflation solved. Another puzzle in cosmology was the flatness problem. The flatness problem comes from the fact that the geometry of the universe seems to be flat. By flat, we mean that the universe appears to have no significant curvature. If the density of matter in the universe were slightly greater, the universe would eventually collapse in on itself. If the density were slightly lower, the universe would expand forever and never form galaxies or stars. The current density of the universe is just right. But how did it get that way? Why does the universe appear to be perfectly balanced, as if it's fine-tuned for life and structure? Inflation solves the flatness problem by proposing that, during the brief period of rapid expansion, the universe stretched so much that any initial curvature was stretched out. Even if the universe started with a slight curvature, inflation would have driven it to near-perfect flatness. This idea explains why the observable universe today looks so uniform and balanced. Inflation also provides an explanation for the large-scale structure of the universe. After inflation ended, the universe continued to expand, but now the energy from inflation had been converted into matter. Small quantum fluctuations in the density of the universe were stretched during inflation and became the seeds for the formation of galaxies, clusters of galaxies, and even the large cosmic voids we see in the universe today. These tiny fluctuations in the density of matter became amplified over time as gravity began to clump matter together. One of the most remarkable aspects of inflation is that it suggests the universe may be part of a larger multiverse. In the standard Big Bang model, the universe started from a single point and expanded into what we now observe. But inflation suggests that this process might be happening continuously in other regions of space, creating an infinite number of bubble universes that each expand and evolve independently. These universes could have different physical properties, possibly with different laws of physics, different types of matter, and different dimensions of space. The idea of the multiverse is still speculative, and while it raises fascinating possibilities, it also leads to new questions. If our universe is just one bubble in a multiverse, what happens to the other bubbles? Could they interact with each other? Or is each universe completely isolated? Some theories suggest that the inflationary process could create new universes as it continues, while others suggest that our universe might be the product of a random quantum fluctuation in a larger eternal cosmic sea. Another question that remains unanswered is what triggered inflation in the first place? What caused the energy to suddenly expand so rapidly? In the early universe, all the energy that we observe today was contained in the inflaton field, which was a quantum field of energy that drove inflation. But what set the inflaton field into motion? Some theories suggest that the energy could have come from a quantum fluctuation, while others speculate that the inflaton field was part of a larger, unknown mechanism in the universe. But for now, the true cause of inflation remains a mystery. As inflation came to an end, the energy in the inflaton field didn't simply vanish. Instead, it transferred into the creation of particles, leading to the reheating phase of the universe. During reheating, the universe was filled with a dense, hot soup of particles, and as it cooled, atoms formed, eventually leading to the creation of stars, galaxies, and all the structures we see today. Though inflation happened in the distant past, it leaves a profound legacy on the universe. The fundamental structure of the cosmos, the cosmic web of galaxies, clusters, and voids, was shaped by the tiny quantum fluctuations that were stretched to vast scales during inflation. The uniformity of the universe and the delicate balance of its physical properties can be explained by inflation, as can the remarkable flatness we observe today. In conclusion, cosmic inflation is a concept that transformed our understanding of the universe's earliest moments. It not only solved some of the most pressing puzzles in cosmology, such as the horizon and flatness problems, but it also opened up new avenues of exploration. The theory suggests that the universe expanded exponentially in a fraction of a second, setting the stage for the creation of galaxies, stars, and the very matter we are made of. Inflation has led to new theories about the multiverse, quantum fluctuations, and the true nature of space-time itself. While there is still much we don't understand, the idea of inflation continues to shape the way we think about the origins of the universe and the fundamental laws that govern it. Whether inflation was a one-time event or is part of a larger, ongoing process is a question that will continue to drive scientific inquiry for generations to come. But how did this rapid expansion happen? Why did it stop? And what exactly triggered it? That's where things start to get even more complicated and even more fascinating. If you're enjoying this deep dive, hit that like button. And don't forget to subscribe to us. Let's continue now. The mechanics of inflation, what powered the expansion? To understand how inflation powered the rapid expansion of the universe, we must first dive into the intricacies of the early cosmos and the mechanisms behind this extraordinary event. Inflation theory posits that during the first moments of the universe, space itself expanded exponentially, much faster than the speed of light. This expansion is thought to have been driven by a mysterious energy field known as the inflaton field. The inflaton field is one of the most speculative and elusive concepts in modern cosmology, and its exact nature remains a subject of intense study and debate. Yet it plays a crucial role in explaining how the universe went from a minuscule, dense state to the vast, complex system we observe today. The mechanics of inflation revolve around the behavior of this inflaton field, which is believed to have been present in the very early universe. Just as the Higgs field is responsible for giving particles their mass, the inflaton field is theorized to have been responsible for causing the rapid expansion of the universe in the very first moments after the Big Bang. At the heart of this process is the idea that this field's energy was stored in such a way that it could release vast amounts of energy, causing space itself to stretch. But how exactly did this energy manifest itself, and what caused inflation to end? When the universe was born, it was an incredibly hot and dense soup of particles, radiation, and energy, existing within a volume smaller than a pinhead. Under these conditions, the usual rules of physics as we understand them today did not apply. The temperatures were so extreme that the forces governing the behavior of matter were unified into a single, incredibly powerful force. The forces of gravity, electromagnetism, and the nuclear forces, strong and weak, were essentially one. The early universe was in a state of chaos, dominated by quantum fluctuations, and the forces were not distinct from one another. This unification is often referred to as the superforce era, where the distinctions between these forces were blurred. As the universe began to cool and expand, the superforce began to separate into the four forces we know today. However, despite this chaotic environment, the universe remained remarkably homogeneous. Quantum fluctuations were small, and the distribution of matter and energy was even. But as we look deeper into these fluctuations, we find the seeds of something much more significant, the pattern that would eventually grow into galaxies, stars, and all the other structures we now observe. But why did this homogeneity exist? What ensured that the universe looked so uniform? This is where inflation theory enters the picture. Inflation proposes that the very early universe expanded exponentially, blowing up from a tiny region to a much larger one in an extraordinarily short period. In fact, inflation theory suggests that the universe grew by a factor of at least 10^26 times in less than a trillionth of a second. This expansion happened so quickly that the distance between even the farthest points in the universe increased by unimaginable amounts in a fraction of a second. Space itself stretched, meaning that the points that were once very close to each other became vastly distant in no time at all. This rapid expansion can be likened to blowing up a balloon. Imagine if you could stretch the surface of the balloon at a rate faster than the speed of light, so that the distance between 2 points on the surface increased exponentially in the blink of an eye. While the material of the balloon itself would stretch, it is the surface, the very fabric of space, that would be rapidly expanding. During this inflationary period, any quantum fluctuations in the fabric of space would be stretched out to enormous scales. These fluctuations became the seeds for the galaxies and clusters of galaxies we see today. However, it's important to note that this stretch of space was not the same as the motion of matter within space. Space itself was expanding, while the matter within it stayed largely the same, apart from the energy released by the field driving inflation. The key to this inflationary expansion was the energy that powered it. This energy came from the inflaton field, which permeated the early universe. The inflaton field is a hypothetical energy field that acted like a form of cosmic gas. It's thought that this field was incredibly dense in the first moments of the universe's existence, and as it began to evolve, it triggered the rapid expansion. This energy field was not uniform across the universe, but rather fluctuated in certain regions, creating pockets of higher or lower energy. These fluctuations are believed to have had a significant impact on the development of the large-scale structure of the universe. As inflation stretched space itself, these fluctuations were stretched too, ultimately becoming the imbalances in density that would later grow into stars and galaxies. One of the key characteristics of the inflaton field is that it has a potential energy associated with it. This potential energy is what drove the universe's expansion. In simple terms, the potential energy of the field acted like a kind of stored energy that, when released, caused space to stretch. The mechanism of this release is still the subject of much speculation, but one idea is that the energy from the inflaton field decayed, transferring its energy into particles. These particles were created in an event called reheating, which marked the end of inflation and the beginning of a more familiar universe filled with matter and radiation. But how does this field release its energy and cause inflation? To understand this, we need to take a look at how fields behave in quantum mechanics. In the early universe, the inflaton field existed in a quantum state, meaning that its energy was not continuous but quantized. The field would have undergone fluctuations, just as other quantum fields do. In some regions, the energy density of the field would have been higher, and in others, it would have been lower. These differences in energy density would have caused the field to evolve in different ways, affecting the rate of inflation in different regions. In regions where the energy density was particularly high, the universe would have expanded at an even more rapid rate. As the universe expanded exponentially, the differences in energy density would have become even more pronounced. This rapid expansion ensured that the universe would be smooth and homogeneous on large scales, while still preserving the fluctuations in energy density that would grow into the large-scale structure of the cosmos. Despite the amazing expansion of space, the universe didn't expand forever at this rate. Eventually, the energy from the inflaton field began to decay, transferring its energy into particles. This transition marked the end of inflation. But why did inflation stop? What caused the energy of the inflaton field to convert into particles and radiation? This is still an open question in cosmology, and scientists are working hard to understand it. One possibility is that the decay of the field's energy was triggered by quantum processes that are still poorly understood. Another possibility is that the energy of the inflaton field simply ran out, causing inflation to cease. However, the end of inflation marked a significant turning point in the universe's development, as it allowed the universe to cool and matter to form. Once inflation ended, the universe entered a phase of rapid but slower expansion. This slower expansion, known as the reheating phase, allowed the energy released by the decaying inflaton field to create particles such as quarks, leptons, and photons. These particles, in turn, began interacting with one another, eventually forming the first atoms and the building blocks of matter as we know it. Though inflation ended, its effects lingered. The fluctuations in the energy density of the universe, created by the inflationary expansion, provided the seeds for the formation of galaxies. These fluctuations led to small variations in the distribution of matter, which were amplified over billions of years by gravity, eventually creating the large-scale structures we observe today. These fluctuations were critical in shaping the universe, and they are still detectable today in the cosmic microwave background radiation, a faint glow that permeates the entire universe. Inflation also provides a solution to a number of cosmological problems. For example, it explains why the universe appears so flat and homogeneous. The rapid expansion stretched out any curvature in the universe, making it appear nearly flat on large scales. It also provided a mechanism for the universe's uniformity, explaining why distant regions of space are so similar, despite the fact that light from those regions hasn't had enough time to travel between them. The concept of inflation also leads to a number of speculative ideas, particularly the theory of the multiverse. According to some versions of inflation theory, inflation didn't just occur once. Instead, it could have occurred in multiple regions of space, each creating its own bubble universe. These bubble universes could have different physical properties, laws of physics, or even constants, leading to an infinite number of possible universes in a vast multiverse. While this idea is still speculative and controversial, it opens up intriguing possibilities for understanding the fundamental nature of reality. Despite its elegance and power, inflation theory leaves many questions unanswered. What exactly triggered the inflationary period in the first place? Why did it stop? What caused the energy of the inflaton field to decay into particles? While we've learned a great deal from inflation theory, it is clear that there is still much more to discover about the early universe and the mechanisms that drove its rapid expansion. Inflation remains one of the most important and mysterious aspects of cosmology, and its full implications are still unfolding as scientists push the boundaries of our understanding of the universe's origins. The scale of inflation, a mind-boggling expansion. The scale of inflation is one of the most mind-boggling aspects of the universe's early expansion, and grasping its magnitude requires stepping far outside the realm of everyday human experience. To understand the true extent of inflation, it helps to picture it in a way that's completely counterintuitive to how we think about the universe. The basic idea behind cosmic inflation is that the universe expanded exponentially, not just quickly, but at a rate that would make our current understanding of speed seem almost laughable. In fact, it's not about speed at all, but about space itself, stretching and growing at a rate unimaginable to us. Inflation occurred so rapidly that it didn't simply expand space, it inflated the fabric of space-time itself, reshaping the universe in a way that still impacts everything we see around us today. Now picture this. In the first moments after the Big Bang, before inflation began, the entire universe was packed into a space smaller than an atom, a microscopic point that contained all of the energy, matter, and the fundamental forces of nature. This point was so dense and hot that space-time itself couldn't even be properly described. The laws of physics as we know them, relativity and quantum mechanics, began to clash. The conditions were extreme to the point of incomprehensibility. But at the moment inflation began, everything changed. A small region, one smaller than the size of a proton, would expand faster than the speed of light. This isn't just a metaphor or an exaggeration. The universe actually grew exponentially, doubling in size not just once but many times, and it did so in a fraction of a second. In less than 10⁻36 seconds, the universe increased its size by a factor of 10 to the 26, or 100 quadrillion times. To make sense of this, consider the scale of this growth in a way that's almost absurd. Imagine having a balloon, a tiny one no bigger than a speck of dust, and inflating it so rapidly that within the blink of an eye, it's as big as our observable universe. The universe didn't just grow incrementally, it grew instantaneously. The process was so rapid that distances between particles and energy fields that were once incredibly close were suddenly stretched out far beyond the limits of what we could measure. Space, not just matter, was stretching, making it seem as though the universe was exploding. But it wasn't an explosion, because an explosion needs a center, a point from which things fly out. Inflation, on the other hand, wasn't about things moving outward from a point. It was the space itself that was expanding. This kind of rapid expansion isn't just a little bit faster than we're used to. It's so fast that it defies everything we know about physics. When we talk about the speed of light being the fastest thing in the universe, we are correct in the context of matter traveling through space. But during inflation, it wasn't the matter that was moving faster than light. It was the very fabric of space-time stretching so quickly that, to an outside observer, distances were collapsing in on themselves or expanding to unfathomable sizes, all within fractions of a second. The concept of moving doesn't even apply because space itself wasn't just expanding at the speed of light. It was expanding at many times that speed without violating any of the rules of physics, simply because nothing in the universe was technically moving faster than light. It was space itself that was changing. To put this into a more familiar context, think about something much smaller and more manageable, a sheet of paper. If you were able to fold the paper in half and keep folding it again and again, you'd see that with each fold, the paper doubles in size. Now imagine you're able to do this over and over again, folding the paper 30 times. What you'd see is the paper growing to astronomical proportions. After 10 folds, the paper might be the size of your desk. After 20 folds, the size of your house. And if you could somehow manage to keep folding it 30 times, the paper would extend beyond the width of the solar system. You could think of the universe during inflation as the piece of paper, being folded over and over again so that, in the blink of an eye, it expanded from subatomic to a size that exceeds anything our human brains can truly comprehend. But the key point here is that it wasn't just about stretching a small space. The real significance of inflation was that it set the stage for everything else. The extreme rate at which inflation occurred flattened the universe, essentially making it uniform across enormous distances. The random quantum fluctuations, tiny, almost imperceptible differences in energy, were stretched out to vast scales. These fluctuations became the seeds for the galaxies, clusters of galaxies, and large-scale structures we see today. Without inflation, there wouldn't have been enough time or space for these fluctuations to grow large enough to create the universe we see. These imperfections became the basis for everything from the stars and planets to the dark matter and dark energy that make up the fabric of the cosmos. The fact that inflation also solved several problems that had plagued cosmologists, such as the horizon problem, the question of how distant parts of the universe could have had the same temperature despite being far apart, further illustrates the scale and impact of inflation. If the universe had expanded gradually, matter in one region would have been unable to communicate with another region, resulting in very different conditions. But inflation ensured that every point in the universe was once close enough to be in thermal equilibrium, leading to a uniform temperature across vast stretches of space. The smoothness of the cosmic microwave background radiation, the afterglow of the Big Bang, is one of the most compelling pieces of evidence that inflation happened as theorized. To fully appreciate the scale of inflation, let's zoom out from the small details and think about what it means for the structure of the universe. If inflation hadn't occurred, the universe might look drastically different. Instead of the expansive, ordered structures of galaxies and galaxy clusters, we might have a much more chaotic universe, with clumps of matter scattered unevenly across vast, empty spaces. Inflation allowed the energy from the initial chaos to smooth out and form the larger structures that make up the universe's cosmic web. The fact that the universe is not just vast but also incredibly uniform, with galaxies distributed along a cosmic web of filaments and voids, can all be traced back to the rapid expansion that occurred during inflation. What makes inflation even more fascinating is that it didn't stop at creating a smooth, uniform universe. The exponential growth left a lasting imprint on the fabric of space-time. Even today, the effects of inflation can be seen in the way galaxies are distributed across the universe. These distant regions, separated by billions of light-years, were once part of the same small, uniform region before they were stretched apart. The small fluctuations in density that inflation caused were stretched so far that they became the seeds of stars, galaxies, and other cosmic structures that began to emerge as the universe cooled down and matter began to form. In fact, the observable universe, roughly 93 billion light-years across, represents only a tiny fraction of what was actually inflated. Beyond what we can see, there's likely much more universe that we'll never be able to observe, simply because the space between us and those distant regions has expanded beyond the limit of what light can reach. This raises another fascinating question. Could inflation be happening even now in other regions of the universe, creating entirely new universes, each with their own physical properties? The idea of a multiverse, where inflation continues indefinitely, is still speculative, but it's one of the many possibilities that stem from the theory of inflation. Inflation's scale wasn't just about creating a uniform universe, however. The sheer speed at which space expanded meant that the universe was constantly evolving. As the universe cooled after inflation stopped, the energy from inflation decayed into particles, setting the stage for the formation of matter. These early particles, quarks, electrons, and other fundamental particles, were created during this phase, setting in motion the creation of atoms, stars, and galaxies. This process, known as reheating, brought an end to the inflationary period and began the era where the universe started to resemble the one we live in today. However, the legacy of inflation doesn't just reside in the early formation of the universe. It continues to impact us today. The distribution of galaxies, the structure of clusters, and even the rate of expansion we see in the universe are all influenced by the way the universe expanded so rapidly in those early moments. The signature of inflation is still embedded in the cosmos, offering clues that future generations of scientists will continue to unravel. The scale of inflation remains one of the most mind-boggling ideas in cosmology, forcing us to rethink everything we know about the universe's origins. It expanded the universe from smaller than an atom to a size far beyond anything we can truly comprehend. And in doing so, it not only shaped the cosmos as we see it today, but also left behind a universe with an infinite number of possible discoveries. Is inflation still happening? The multiverse theory. One of the most mind-boggling and controversial aspects of the theory of cosmic inflation is the idea that inflation may not have stopped at all. While most of us believe that inflation happened just in the very early moments of our universe, some theories propose that inflation could still be going on in other parts of the cosmos, possibly creating a vast number of bubble universes, which is where the concept of the multiverse comes in. The notion of the multiverse is far from a simple extension of the inflationary theory. In fact, it introduces one of the most profound and radical ideas in modern physics, that our universe may not be the only one. Instead, it could be just one of many universes, each with its own set of physical laws, properties, and constants. The multiverse is a speculative theory, but its roots lie in the inflationary model, which suggests that, in the early moments of the universe, space expanded so quickly that it stretched out any irregularities or fluctuations in a smooth, uniform manner. But in a universe as vast as ours, the idea that inflation could have only occurred in one place seems almost too limited. In the most speculative of scenarios, inflation could have occurred eternally, with new regions of space constantly inflating in a never-ending process. If inflation is indeed eternal, then every time inflation occurs, it would create a new bubble of space-time. These bubbles would each develop into their own individual universes, each with different properties. These universes would be completely separate from each other, disconnected in every way, and possibly governed by different laws of physics. This type of eternal inflation would be an ongoing process, continuously producing bubbles of new universes throughout the fabric of space-time. The universes themselves would have different starting conditions, and they would evolve in completely different ways. For instance, one bubble might give rise to a universe where gravity is much stronger than in our own, while another might create a universe where the fundamental constants of physics are completely different. In this view of the multiverse, our own universe is just one bubble in an infinite sea of bubbles. It would be like a tiny droplet in an endless ocean of universes, where each droplet is its own unique universe with different properties and histories. Some theorists argue that this multiverse model could explain many of the perplexing questions we still have about our own universe, such as why the fundamental constants of nature are so finely tuned. If there are many universes with different constants, we might just happen to live in one where the values are just right for life to exist. But how did these bubbles come to be? In the inflationary model, the universe began as a tiny, hot, and dense point that rapidly expanded. As inflation drove the expansion, regions of space-time became stretched out, causing tiny quantum fluctuations to be magnified into huge differences in energy. These fluctuations are believed to have created the seeds for the galaxies, stars, and other cosmic structures that would later form. But in the case of eternal inflation, these fluctuations didn't just happen once. Instead, they could have continued to occur, creating new bubbles of space-time each time. This would mean that inflation is not a one-time event, but a continuous process that never ends. The idea of eternal inflation is not just theoretical. There is some indirect evidence that supports the possibility of a multiverse. One of the key pieces of evidence comes from the study of the cosmic microwave background, CMB, which is the afterglow of the Big Bang. The CMB is a faint radiation that fills the entire universe and provides a snapshot of the early universe just a few 100,000 years after the Big Bang. Scientists have studied the CMB in great detail, looking for patterns or anomalies that might reveal information about the early history of the universe. Some researchers believe that certain patterns in the CMB could be the result of interactions between our universe and other universes in the multiverse. These patterns are subtle, and their significance is still debated, but they hint at the possibility that our universe may be part of a larger cosmic structure. In addition to the CMB, there are other pieces of evidence that suggest the multiverse theory could be more than just a speculative idea. For example, some cosmologists argue that the apparent fine-tuning of the universe is best explained by the existence of many different universes. If there are a vast number of universes, then it's not so surprising that one of them would have the right conditions for life. In this way, the multiverse offers a natural explanation for why our universe appears to be so perfectly tuned for the existence of life. Without the multiverse, the fine-tuning of the constants of nature might seem like an incredibly improbable coincidence. But if there are an infinite number of universes, then the existence of one like ours becomes much more likely. However, the idea of the multiverse is not without its critics. One of the biggest criticisms of the multiverse theory is that it is essentially untestable. If there are other universes out there, they are completely disconnected from ours and cannot be observed or measured in any way. This raises the question of whether the multiverse is a scientific theory at all. Many scientists argue that for a theory to be considered scientific, it must be testable and falsifiable, meaning that it should be possible to conduct an experiment or make an observation that could prove the theory wrong. Since the multiverse theory deals with universes that we cannot access or observe, some critics claim that it falls outside the realm of science and into the realm of philosophy or speculative fiction. Despite these criticisms, the idea of the multiverse has gained significant traction in the scientific community, particularly among those who study cosmology and theoretical physics. Some physicists argue that even though the multiverse may not be directly observable, there could still be indirect ways to test its existence. For example, if our universe is part of a larger multiverse, it's possible that we might observe subtle effects or anomalies that could hint at the presence of other universes. These effects could be seen in the CMB, in the distribution of galaxies, or in other aspects of the universe's structure. While these ideas are still highly speculative, they open up exciting possibilities for future research and exploration. One of the most fascinating aspects of the multiverse theory is that it challenges our fundamental understanding of reality. For centuries, humans have believed that our universe is the only one that exists. The idea that there might be an infinite number of other universes, each with its own set of physical laws and constants, is both awe-inspiring and humbling. It suggests that the cosmos is far more vast and complex than we ever imagined. And if there are truly an infinite number of universes, it raises profound questions about the nature of existence itself. Are we just one of countless other civilizations in an infinite sea of possibilities? Is the universe we live in just one possibility among many, or is it the only one that could have ever existed? These are the questions that the multiverse theory forces us to confront, and they challenge our deepest assumptions about the nature of reality. Despite the excitement that the multiverse theory generates, there are still many unanswered questions. If inflation created a vast number of universes, how did it all start? What triggered the very first instance of inflation, and why did it happen? These are questions that remain elusive, and it's unclear whether we will ever have answers to them. However, the multiverse theory provides a framework for understanding the universe in a way that goes beyond our immediate observations. It suggests that the universe we live in is just one piece of a much larger puzzle, and that the answers to the most profound questions may lie beyond our current understanding. In conclusion, the multiverse theory is one of the most exciting and mysterious ideas in modern cosmology. While it remains speculative and untested, it offers a new way of thinking about the universe and its origins. The idea that inflation could be an eternal process, constantly creating new universes, challenges our basic assumptions about the nature of reality and opens up new possibilities for understanding the cosmos. While the multiverse may never be directly observable, its implications are far-reaching, and it invites us to think about the universe in ways we never have before. Whether or not the multiverse is real, it pushes the boundaries of science and invites us to explore the deepest mysteries of existence. What caused inflation to stop? Now we get to the tricky part. What triggered inflation to stop? The end of cosmic inflation remains one of the most intriguing and complex puzzles in modern cosmology. For most of the history of our universe, inflation lasted just a tiny fraction of a second, far less than the blink of an eye. Yet, in that minuscule amount of time, the universe expanded by an astonishing factor, from being smaller than a subatomic particle to roughly the size of a grapefruit, setting the stage for the more gradual expansion that continues to this day. The question, however, is not just what caused inflation to begin, but what triggered its cessation. The process that caused inflation to stop is referred to as reheating or thermalization, and it marks a dramatic shift in the behavior of the universe. But before we explore how inflation stopped, we need to understand the context of how it began. Inflation, as proposed by Alan Guth and others, was driven by a hypothetical field known as the inflaton field. This field was responsible for the universe's rapid expansion during the inflationary era. The inflaton was not a type of matter we can detect directly, but rather an energy field that existed in the early universe. In simple terms, it acted like an engine, driving space to stretch at an exponential rate. As the universe inflated, it was filled with an extremely high energy state. The energy in the inflaton field drove the expansion, pushing space apart at speeds faster than the speed of light itself. This rapid expansion stretched out quantum fluctuations in the fabric of space-time, creating the seeds of galaxies, stars, and cosmic structures that we see today. But as the universe expanded and cooled, the inflaton field itself began to lose energy. And as it did, inflation couldn't continue indefinitely. The critical question becomes, what stopped inflation from going on forever? At the heart of this issue lies the concept of vacuum energy. During inflation, the universe existed in what is known as a false vacuum state. This is a state of high potential energy where the universe is metastable, meaning it is in an unstable equilibrium that cannot last forever. The inflaton field filled with energy was in this false vacuum, and as the universe expanded, this energy drove the rapid inflation. However, this false vacuum was bound to decay. The decay of this energy in the false vacuum led to the transition to a more stable state, known as the true vacuum. When the false vacuum decayed, the universe shifted from this unstable state to a more stable one, and this phase transition triggered the end of inflation. This transition, however, wasn't like flipping a light switch. It was a gradual process. The decay of the false vacuum resulted in the conversion of vacuum energy into particles and radiation, effectively reheating the universe. This is what we refer to as the reheating phase, and it's crucial because it marks the point at which the universe shifted from being dominated by inflationary expansion to being filled with matter and radiation, setting the stage for the formation of atoms, stars, and galaxies. To picture this more clearly, imagine the universe as a giant, superheated pot of soup. During inflation, the soup expanded rapidly, with all the ingredients stretched out to an almost unimaginable size. But eventually, the pot ran out of the initial energy needed to keep the soup bubbling. The energy from inflation began to dissipate, and this caused the universe to cool down and settle into a state of lower energy, much like how a boiling pot cools after the heat is turned off. However, as the soup cooled, it didn't just stop. The energy that once fueled inflation began to condense and coalesce into particles of matter, which led to the creation of the fundamental building blocks of the universe. This was the moment when the energy from the inflaton field turned into the matter and radiation that would eventually form stars, galaxies, and all the matter in the universe as we know it. In simpler terms, inflation ended when the energy of the inflaton field decayed into particles. But this decay didn't happen in one abrupt moment. Instead, it happened through a process known as quantum tunneling. Quantum tunneling is a strange phenomenon where particles can tunnel through energy barriers that they shouldn't theoretically be able to pass. In the case of inflation, the energy barrier between the false vacuum, the high energy state, and the true vacuum, the more stable, lower energy state, was crossed through quantum tunneling. This transition triggered the release of energy, which became the radiation and particles that flooded the early universe, filling space with energy in the form of radiation and allowing particles to form for the first time. One of the big questions scientists have been grappling with is the precise nature of the mechanism behind inflation's end. What exactly happened during this decay process? One theory suggests that the decay of the false vacuum was governed by the properties of the inflaton field itself. The inflaton's potential energy was slowly converted into kinetic energy, and when the energy dissipated to a certain point, inflation ended. However, this process didn't happen in isolation. The transition from the false vacuum to the true vacuum created turbulence in the energy field, resulting in the creation of particles, and this process led to what we now call reheating. Reheating is one of the most important moments in the history of the universe because it set the stage for everything we see today. The universe went from a hot, dense, and energy-filled state into a cooler, matter-dominated one. At the end of inflation, the universe was still incredibly hot, far hotter than any star we see today. But now, instead of just a vast, empty void filled with energy, the universe began to cool, and matter began to condense. This cooling allowed the formation of quarks, gluons, and other subatomic particles that would eventually combine to form protons, neutrons, and eventually atoms. However, as much as we know about the reheating phase, there's still much we don't understand. Scientists are still working to unravel exactly how the energy from inflation turned into the particles that created the universe as we know it. The problem lies in the fact that the physics of inflation is governed by a set of conditions that are hard to replicate or even observe directly. The universe was in such a high-energy state during this time that we don't have the technology to simulate those conditions on Earth. We can't recreate the temperature and energy of the early universe in a laboratory, which makes studying this period incredibly difficult. In addition, the exact details of what happened during reheating depend on the properties of the inflaton field itself, which remains elusive. We don't have direct evidence for the inflaton or its exact behavior. This means that much of the work being done to understand inflation's end is based on theoretical models and observations of the universe's structure today. While these models have been successful in explaining a lot of what we see, we still don't know everything about the mechanism behind inflation's cessation. Some physicists suggest that the end of inflation could have been influenced by the interactions of other fields in the early universe, or that the energy from the inflaton field could have decayed in a more complex, multi-stage process. The true nature of this transition may remain one of the greatest unanswered questions in cosmology. One of the most fascinating possibilities raised by inflation is the idea that it might not have ended everywhere at the same time. According to the theory of eternal inflation, inflation might continue in some regions of the universe, creating new bubble universes. These bubble universes could have different physical laws, different constants, and different histories. In this scenario, our universe is just one bubble in a larger multiverse, where inflation continues eternally in different regions of space, each bubble universe expanding at its own rate and following its own rules. This concept raises even more questions about the true nature of the cosmos and how our universe fits into a broader multiverse. As it stands, we don't know exactly what caused inflation to stop, but we do know that the end of inflation marked the beginning of the universe as we know it. It's a moment in cosmic history that set the stage for the formation of galaxies, stars, and the elements that make up the world around us. Whether the end of inflation was triggered by the decay of the inflaton field, quantum tunneling, or some other mysterious process, it was a key event in the evolution of the universe. In the end, the cessation of inflation didn't just signify the end of rapid expansion. It marked the birth of a new era in the universe's history, one that would see the formation of structure, the development of matter, and the emergence of the complex and dynamic cosmos we observe today. And while the specifics of how inflation ended remain a topic of debate and exploration, we can be certain that it was a defining moment in the story of the universe, a moment that continues to shape everything we see around us. The idea of inflation revolutionized our understanding of the early universe. Without inflation, we wouldn't be able to explain why the universe looks so uniform, why it seems so flat, or why it contains the vast structures we observe. Inflation is the key that unlocks the mystery of the universe's earliest moments. In the few moments it took for inflation to unfold, the universe transformed from a tiny, hot, dense state into the sprawling cosmos we see today. It set the stage for the formation of galaxies, stars, and planets, and for the eventual emergence of life itself. And while inflation itself may have ended billions of years ago, its legacy continues to shape the universe in ways we're only beginning to understand. What's most exciting is that inflation has opened up new avenues of exploration for cosmologists and physicists. We've already learned so much, but there's still so much more to discover. Whether or not we ever fully understand the ultimate cause of inflation, one thing is clear: the universe is much stranger and much more fascinating than we ever imagined. The birth of forces. In the earliest moments of the universe's life, everything was chaotic. The universe was in a state of extreme density and temperature, so hot and dense that the laws of physics as we know them couldn't even function properly. In the first few fractions of a second, the universe was like a single boiling cauldron of raw energy, a primal soup where space, time, and matter hadn't yet begun to form the structures we recognize today. Yet during these chaotic first moments, something extraordinary was happening. The fundamental forces of nature, the very building blocks of everything we know, began to take shape. The superforce, unity before separation. In the very first moments of the universe, everything was radically different from what we understand today. Imagine a time when the entire universe was squeezed into an incredibly small and dense point. a point so tiny that it makes the smallest particles we know of, like atoms or even subatomic particles, seem vast in comparison. The universe at this stage was not only tiny, but incredibly hot. Temperatures were so extreme that normal matter, as we understand it, didn't even exist. It was a time when the laws of physics as we now know them were still evolving. During this moment, the universe was not a collection of individual forces, particles, or matter. Instead, all the fundamental forces, gravity, electromagnetism, and the nuclear forces were fused together into a single entity. This state of unity is referred to by scientists as the superforce. This unified state is something that is difficult for us to truly imagine because, in our everyday lives, we experience the forces as separate, distinct entities. We can see gravity pulling things downward, experience the effects of electromagnetism in the form of electricity and magnetism, and we are familiar with the strong and weak nuclear forces that govern the behavior of subatomic particles. But in the earliest universe, these forces were not separate. They were united as one. This state of unity was not just a theoretical idea. It was the state of reality. In this era, everything in the universe was governed by a single force, a singular field of energy that did not differentiate between the forces we now know as gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. To understand the magnitude of this concept, we need to imagine a time before the very concept of space and time had fully emerged. The universe was not an expanse with stars, planets, or galaxies. It was an incredibly hot, dense soup of energy and particles that existed in a state of chaos. In this soup, there was no distinction between the forces we rely on every day. The distinctions between the forces that now control everything were not yet made. But how did this superforce come to be, and what did it mean for the universe? In the very beginning, the universe was essentially a kind of primordial energy field. The temperature was so high and the energy density so intense that particles could not yet form. Instead, the universe was filled with a hot, dense plasma of quarks and gluons. These are fundamental particles that, under normal conditions, form protons and neutrons. But in this early universe, the temperatures were so high that these particles were not bound together into matter. The energy in the universe was so intense that particles were continuously being created and destroyed at an astonishing rate. But during this time, the universe was still unified as a single force. For a moment, imagine that all the forces in the universe were packed into one single, unified force. They were all blended together in a manner that defies the typical physical laws we experience. It was as if the universe had not yet decided how to express itself. All the cosmic ingredients, gravity, electromagnetism, and the nuclear forces, existed in a strange, unified way. This was a state of unbroken symmetry where the forces were one and indistinguishable. It was a time when, as we look back now, the nature of reality as we understand it was still in flux, still emerging from a chaotic, primordial condition. Now, you might be wondering how we know about this stage of the universe. The answer lies in a combination of theory and observation. One of the fundamental ideas in physics that we rely on to understand the early universe comes from something known as the Standard Model of particle physics. This model describes the behavior of the fundamental particles and forces we encounter in the universe today. It is based on years of experimental evidence and provides a framework that has helped scientists explain the behavior of the universe at both small and large scales. But here's the interesting part. This model has a fundamental problem when it comes to the very beginning of the universe. The Standard Model works well for understanding the forces and particles we see today, but it doesn't fully explain what happened during the first moments after the Big Bang. This is because the forces were so tightly unified in the beginning that they cannot be described by the Standard Model alone. To account for this, scientists rely on more speculative theories, such as Grand Unified Theory, GUT, which tries to explain how all four forces of nature were united in the early universe. GUT proposes that in the early moments of the universe, all the forces were combined into a single force, and only as the universe began to cool did the forces begin to break apart. But before the forces broke apart, they were so intertwined that they were indistinguishable. In this unified state, the different types of forces, Gravitational, electromagnetic, and the strong and weak nuclear forces did not behave as distinct entities. Instead, they were one single unified force. In this state, the universe was incredibly small, and it was also unimaginably hot, meaning that any matter or even stable particles could not exist. Instead, the energy that filled the universe took the form of radiation, creating a hot soup of subatomic particles constantly in motion. However, as this energy field expanded, cooling gradually, the forces started to behave in more familiar ways, each splitting off into its own domain. The temperature dropped, and as it did, the superforce began to differentiate. But this differentiation wasn't instantaneous. The forces split gradually, beginning with gravity. Gravity was the first force to separate from the unified field. As the universe cooled, gravity became distinct, and the force of gravity began to influence the matter in the universe. Gravity, in this case, wasn't just the force that attracts objects to each other. It was the force that governed the very fabric of space and time itself. Gravity became the dominant force that shaped the large-scale structure of the universe. It pulled matter together, eventually forming the galaxies, stars, and planets we now see in the cosmos. Following the separation of gravity, the other forces began to break apart. Electromagnetism, which governs everything from the behavior of light to the interactions between charged particles, began to separate next. As the universe cooled further, the strong nuclear force, which holds protons and neutrons together inside atoms, and the weak nuclear force responsible for radioactive decay, also began to emerge as distinct forces. Now the forces were no longer unified. Gravity, electromagnetism, the strong nuclear force, and the weak nuclear force were all separate entities, each with its own specific rules and properties. But the transition from the superforce to these individual forces didn't happen in a simple, linear fashion. Instead, it involved a process known as symmetry breaking, which is central to our understanding of the birth of the universe. As the temperature of the universe dropped and space expanded, the previously unified superforce began to break into the forces we recognize today. Each force emerged in its own distinct way, and its influence shaped the development of the universe. What's truly fascinating about this process is that scientists believe that the exact way the forces separated and interacted with one another in these early moments of the universe could hold the key to understanding the deepest mysteries of the cosmos. If we can understand the superforce, how it unified the forces of nature, and how it broke apart to form the universe we know, we might be able to answer questions that have puzzled humanity for centuries. What happened before the Big Bang? Why does the universe behave the way it does? What forces govern the structure of the cosmos, and how did they come to be? The separation of the superforce into distinct forces marked a pivotal moment in the history of the universe. It set the stage for the formation of matter, the creation of atoms, and the eventual emergence of stars and galaxies. Yet, this moment also left us with a profound mystery. If the forces were once united, could they one day reunite? Could there be a deeper level of unification that we have yet to discover? These questions continue to drive modern physics. The search for a theory of everything, a theory that unifies all four fundamental forces, is one of the central goals of physicists today. And while we've come a long way since the early days of the universe, the mystery of the superforce and the fundamental forces it gave rise to remains one of the most profound and tantalizing questions in science. In the grand scheme of things, understanding the superforce is not just a scientific pursuit. It's a journey into the very nature of reality itself. The birth of the forces and the way they interacted in the earliest moments of the universe laid the groundwork for everything that followed. But just as we uncover one layer of the universe's mysteries, new questions arise, pushing us to explore even deeper into the heart of creation. Breaking the symmetry, cooling, and the separation of forces. In the earliest moments following the Big Bang, the universe was a singular, almost incomprehensibly dense and hot space, where the familiar laws of physics didn't yet apply. This state was chaotic and formless, with the entire universe, space, time, and energy, compressed into a tiny volume. The concept of time itself was not fully established, and the idea of distinct physical forces was non-existent. At this stage, all four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were unified as one single force, often referred to as the superforce. This phase was incredibly brief, lasting only a tiny fraction of a second, but during this period, the forces that govern the behavior of everything in our universe were indistinguishable from each other. As the universe began to expand and cool, this unity of forces began to break apart in a dramatic process known as symmetry breaking. The moment when these forces separated marked a crucial point in the universe's evolution, laying the groundwork for the cosmos as we know it today. In simple terms, symmetry breaking is when a system transitions from a state of perfect symmetry to one where distinct parts of it behave differently. It's like taking a perfect sphere and then applying heat or pressure to it, causing it to fracture into different pieces. This breaking of symmetry didn't just affect particles and forces, it fundamentally changed the nature of the universe itself. As the universe cooled after the Big Bang, the intense energy that once kept the forces united started to dissipate. The temperatures were still unimaginably high, but as the universe expanded, things began to change. As the hot, dense plasma began to spread out, the superforce began to lose its cohesion. The first to break away from the superforce was gravity. Unlike the other forces, gravity is unique because it is a long-range force that acts on all forms of matter, from the smallest subatomic particles to massive stars and galaxies. When gravity separated from the superforce, it became the force we are familiar with today, influencing the movement of galaxies, the formation of black holes, and the motion of celestial bodies. Meanwhile, the remaining forces, electromagnetism, the strong nuclear force, and the weak nuclear force, continued to remain intertwined for a brief time. As the universe cooled even further, however, these forces began to unravel. The cooling universe allowed for the distinct characteristics of the forces to emerge. The strong nuclear force, responsible for binding protons and neutrons together within atomic nuclei, became distinct from the electromagnetic and weak nuclear forces. But this process wasn't instantaneous. It was a slow and gradual one, a cosmic dance between energy, temperature, and the fundamental forces. For a very brief time, the electromagnetic and weak forces were so intertwined that they were difficult to separate. As the universe expanded and cooled, the temperature began to drop to a point where the electromagnetic and weak forces started to decouple from one another. This phenomenon is often described as electro-weak symmetry breaking. Before this separation, the electromagnetic force and the weak nuclear force were considered different manifestations of the same force, often referred to as the electro-weak force. But as the universe cooled, the energy that was once required to keep these forces unified became too weak to sustain the unity. At this stage, the universe was still incredibly hot, but as temperatures fell, the electromagnetic force broke off and began to behave independently. The electromagnetic force governs the behavior of charged particles and electromagnetic radiation, including light, and it's the force responsible for electricity, magnetism, and the interaction between atoms and molecules. This force controls everything from the way atoms bond to the way light travels across space. When the electromagnetic force became distinct, it was capable of acting independently, unrestrained by the weak nuclear force, allowing the development of the chemistry and physics we now observe. The weak nuclear force, which governs processes like beta decay and nuclear fusion, also separated around the same time. But unlike electromagnetism, it acts over much shorter distances and has much less influence on the large-scale structure of the universe. However, the weak force is absolutely crucial to the process of nuclear fusion that powers stars, and it governs the behavior of particles in the nucleus of atoms. When the weak force separated from the electromagnetic force, the universe began to evolve into a form that was more recognizable, with different forces governing different aspects of matter and energy. What's remarkable about the process of symmetry breaking is that it wasn't just a random or haphazard event. The way the forces separated and began to behave in distinct ways dictated the laws of physics that would govern everything from the formation of the first atoms to the creation of galaxies. The delicate balance between the forces as they separated would determine the properties of the universe. This process of symmetry breaking was critical for the formation of the universe as we know it, and it laid the foundation for the emergence of mass, particles, and ultimately the formation of stars and galaxies. One of the key events that occurred as symmetry broke was the creation of mass. As the forces began to separate, the universe cooled enough for the newly formed particles to acquire mass. This happened because of the presence of the Higgs field, a field that permeates all of space and interacts with particles to give them mass. Without the Higgs field, particles would have remained massless, and the universe would have been a very different place, one without matter as we know it, without atoms, without stars, and without life. The discovery of the Higgs boson in 2012 provided evidence for the existence of this crucial field, confirming that mass itself was an intrinsic property that was conferred onto particles as they interacted with the Higgs field. As the universe cooled and expanded, these mass-giving interactions set the stage for the formation of matter. Protons, neutrons, and electrons began to form from the simpler, massless particles that had existed before. As the Higgs field interacted with these particles, they began to gain mass, allowing them to form atoms, which would later combine to create stars, planets, and galaxies. This mass acquisition wasn't instantaneous, but it was crucial. Without it, the universe would have remained a chaotic, featureless sea of energy, with no way for complex structures to form. The consequences of symmetry breaking weren't just limited to the forces themselves. As the forces separated, the universe began to take shape in a way that was governed by the distinct behaviors of each force. The strong nuclear force began to hold atomic nuclei together, while electromagnetism allowed for the formation of atoms, and the weak nuclear force played a role in the formation of chemical elements. Gravity, meanwhile, began to take on its familiar role, pulling matter together and shaping the large-scale structure of the universe. One of the most profound implications of symmetry breaking was the eventual development of the cosmic structure we see today. In the earliest moments of the universe, matter was spread out in an incredibly uniform way, but as the forces began to separate, the matter that filled the universe began to interact in ways that led to the creation of stars, galaxies, and even larger structures like galaxy clusters and superclusters. This gradual process of cooling, separating forces, and acquiring mass led to the formation of the universe's first atoms and the creation of the first light. As the universe continued to cool and expand, these processes led to the formation of galaxies and the stars that would eventually give birth to the elements that make up our world. Without the symmetry breaking that occurred in the first moments of the universe, none of this would have been possible. The separation of forces created the conditions for the universe to evolve into the complex and dynamic cosmos we observe today. What makes symmetry breaking so remarkable is that it was not a one-time event, but a continuous process that set the foundation for the universe's development. It's an ongoing phenomenon, one that shaped the universe's evolution from its earliest moments to the present day. Every time a new structure forms, whether it's a star, a galaxy, or even life itself, it's a result of the intricate balance that was first established during this period of symmetry breaking. The forces that separated billions of years ago are still at play today, governing the way matter interacts and shapes the cosmos. This process of symmetry breaking was one of the key moments in the birth of the universe. It wasn't just a simple separation of forces. It was a cosmic turning point that gave birth to the very laws of physics we use to understand the world around us. The way these forces separated and the nature of their interactions laid the foundation for the universe's evolution, allowing it to transition from a hot, dense soup of particles to the vast, organized cosmos we see today. It is a fundamental part of the story of how the universe began, and it remains one of the most profound mysteries in the history of science. In the end, the breaking of symmetry was not just a random event. It was the spark that ignited the universe's evolution. It is the reason we have matter, the reason we have the universe we live in, and the reason we are able to ask the question, how did the universe begin? The Higgs field, giving mass to particles. At the heart of the universe's creation, one of the most essential and puzzling questions was how particles gained mass. In the early universe, during the first few moments after the Big Bang, particles were essentially weightless. They moved at the speed of light and didn't have any of the properties we associate with matter, like mass or weight. Without mass, these particles would have been incapable of forming the matter we know today, from the stars to the planets, and ultimately to us. But how did mass come into existence? This question was one of the biggest mysteries in physics for decades, and the answer came with the concept of the Higgs field, a fundamental aspect of the universe that plays a pivotal role in giving particles mass. To understand how this works, we need to first understand a bit about what mass is and how it behaves in our universe. Mass is a property of matter, one that gives particles the ability to interact with gravity and resist being accelerated. It's an intrinsic characteristic, just like charge or spin. And in the early universe, particles were created as high-energy, massless entities, constantly in motion. They had no weight, no resistance, and moved freely at the speed of light. But as the universe began to cool, things began to change. Particles that were once massless started to acquire mass, and the mechanism responsible for this phenomenon is the Higgs field. The Higgs field itself is invisible and all-pervasive, filling the entire universe. Imagine it as a kind of cosmic molasses, filling the universe and interacting with the particles that pass through it. This field interacts with certain particles in a way that slows them down and gives them mass, making them behave in a way we can recognize as matter. The stronger a particle interacts with the Higgs field, the heavier it becomes. The weaker its interaction, the lighter the particle is. This interaction with the Higgs field is what transforms massless particles into those with mass, and it's what gives the universe its structure. The Higgs field was first proposed in the 1960s by Peter Higgs, a British theoretical physicist, who realized that in order for particles to acquire mass, there had to be a field that permeated the entire universe. This was a groundbreaking idea, as it suggested that the very fabric of space itself was an active participant in creating matter. Higgs, along with several other scientists, introduced this concept as part of the Higgs mechanism, which describes how particles gain mass through their interaction with this invisible field. However, the Higgs field alone wasn't enough to explain everything. Higgs also predicted the existence of a particle, now known as the Higgs boson, that would act as the carrier of the field. Just as photons carry the electromagnetic force, the Higgs boson would carry the Higgs field's effect, making it measurable. In 2012, after years of experiments and searches, scientists at CERN confirmed the existence of the Higgs boson, a monumental discovery that cemented the Higgs field as one of the cornerstones of modern physics. The Higgs boson itself is a special particle. Unlike other force-carrying particles like photons or gluons, which mediate electromagnetic and strong forces respectively, the Higgs boson is associated with mass. Its discovery was a breakthrough in confirming the Higgs mechanism, as it was the missing piece of the puzzle that explained how particles gain mass. The confirmation of the Higgs boson's existence was a monumental moment in physics, confirming that the Higgs field, which was once only a theoretical construct, is real and actively shaping the universe around us. To better understand how the Higgs field works, we can think of it like a thick syrup or molasses that fills the universe. Imagine a group of people moving through a room full of this sticky substance. Some people would move through it more easily, while others would struggle to get through, depending on how much they interacted with the syrup. In this analogy, the people represent particles, and the syrup is the Higgs field. Some particles, like the photon, move freely and don't interact with the field at all, so they remain massless. Other particles, like the W and Z bosons, the carriers of the weak nuclear force, interact with the Higgs field much more strongly, which gives them mass. The more a particle interacts with the field, the more mass it acquires, just as someone who struggles to move through the syrup gets heavier. The Higgs field is essential for creating the universe as we know it. Without it, particles wouldn't have mass, and without mass, there would be no atoms, no molecules, no stars, and no galaxies. The existence of the Higgs field allows particles to interact in a way that forms the matter that makes up the universe. Without mass, matter couldn't exist, and without the Higgs field, mass couldn't be generated. This process is what allows the universe to have the structure it does, from the smallest building blocks of atoms to the vast galaxies scattered across the cosmos. One of the key implications of the Higgs field is its role in the Standard Model of particle physics, which is the theory that describes how all fundamental particles interact. The Standard Model includes everything from the most fundamental particles, like quarks and electrons, to the forces that govern their interactions, such as the electromagnetic force and the weak nuclear force. However, for years, the Standard Model had one glaring omission. It didn't explain why some particles had mass while others did not. The introduction of the Higgs field filled in that gap, providing a mechanism for mass generation that was consistent with all the other forces and particles described by the Standard Model. It's important to note that the Higgs field does not create mass out of thin air. Instead, it works by interacting with particles that are already in existence, slowing them down and giving them the mass they need to interact with gravity and other forces. This is why mass is often thought of as a kind of resistance to the movement of a particle. The Higgs field gives particles the resistance they need to exist as matter. Without this resistance, the particles would just zip around at the speed of light, unable to form the matter we see today. The strength of the Higgs field also has implications for the properties of the universe. The strength of the Higgs field determines how massive particles become. If the Higgs field were weaker, particles would have less mass, and if it were stronger, particles would have more mass. This is why the discovery of the Higgs boson was so important. It confirmed that the Higgs field exists and interacts with particles in a way that aligns with the predictions made by physicists. The exact strength of the Higgs field is crucial for determining how the universe behaves. It affects everything from the formation of galaxies to the structure of matter itself. The discovery of the Higgs boson and the confirmation of the Higgs field were not just triumphs for theoretical physics. They also marked a turning point in our understanding of the universe. The Higgs mechanism is not just a mathematical concept. It is a physical reality that governs the behavior of particles and shapes the universe we live in. It has allowed scientists to answer one of the most fundamental questions in physics: how do particles get mass? But the Higgs field raises even more questions. While we now understand how it works to give particles mass, scientists are still unsure about the exact nature of the Higgs boson itself. Is it the only particle responsible for mass, or are there other fields and particles yet to be discovered? The Higgs boson is the key to understanding how mass works, but it may also be a stepping stone toward discovering new and exciting areas of physics. We know that the universe is far more complex than we currently understand, and the Higgs field is just one piece of the puzzle. In conclusion, the Higgs field is an invisible, all-pervasive force that permeates the universe, interacting with particles to give them mass. This simple, yet profound idea has transformed our understanding of the universe, explaining how particles that were once massless acquire the resistance they need to form the matter we know today. The discovery of the Higgs boson confirmed the existence of the Higgs field and provided us with the final piece of the puzzle in the Standard Model of particle physics. The Higgs field has shaped the universe from the very beginning, and its role in the creation of mass is one of the most important discoveries in the history of science. But as with many things in physics, the Higgs field opens up new questions and challenges, and the journey to fully understand it has only just begun. The strong nuclear force and the weak nuclear force. When we look around at the universe, everything we see is made up of matter. From the smallest grains of sand on the beach to the largest galaxies in the cosmos, all matter is made up of atoms. Atoms themselves are composed of three primary subatomic particles: protons, neutrons, and electrons. While the electron orbits around the atom's nucleus, it is the protons and neutrons inside the nucleus that hold the key to understanding the universe on a fundamental level. But here's the catch. Protons and neutrons are made up of even smaller particles called quarks, and the force that holds quarks together inside protons and neutrons, allowing matter itself to exist as we know it, is the strong nuclear force. The strong nuclear force is the fundamental force that operates at extremely short distances. It's what keeps protons and neutrons bound together in the atomic nucleus, despite the fact that protons are positively charged and therefore naturally repel each other. At first glance, this seems impossible. After all, like charges repel, so how could protons, each carrying a positive charge, be bound together in the same tiny space at the center of an atom? The answer lies in the powerful, almost mind-bogglingly strong force of attraction that operates on incredibly small scales. The strong nuclear force is so powerful that it can overcome the repulsion between like charges and hold protons and neutrons together with tremendous force. The force is mediated by particles called gluons, which are the force carriers of the strong nuclear force, much like photons are the carriers of electromagnetic force. However, unlike photons, which can travel freely across large distances, allowing us to see light for instance, gluons are confined to the extremely small region of the atomic nucleus. This is because they interact with quarks and other gluons within the nucleus, creating what is known as the strong force field, which binds protons and neutrons together. Without the strong nuclear force, atoms would not hold together. Protons would fly apart, and the very structure of matter would collapse. At a fundamental level, everything that is solid, liquid, or gas depends on the interactions between quarks and gluons within the nucleus. The strong nuclear force is what allows the protons and neutrons to remain locked together inside an atom, providing the foundation for all of chemistry and, by extension, all of matter itself. As the universe began to cool after the Big Bang, quarks and gluons combined to form protons and neutrons. But even as protons and neutrons were being formed, the strong nuclear force was still in play, holding everything together. The strong force was a key player in the creation of the first atomic nuclei. These early nuclei, composed of protons and neutrons, eventually went on to form the elements we know today. Without the strong nuclear force, these early nuclei would not have been stable, and the elements necessary for life, carbon, oxygen, nitrogen, could never have formed. In this way, the strong nuclear force has been critical in shaping the very building blocks of the universe. As the universe cooled and expanded, protons and neutrons began to combine to form simple atomic nuclei, like hydrogen and helium. These atomic nuclei formed in the early moments of the universe, around 3 minutes after the Big Bang, during a period known as Big Bang nucleosynthesis. The strong nuclear force helped to create the lightest elements, like hydrogen and helium, in the first few minutes of the universe's existence, while heavier elements like carbon and oxygen would later form inside stars through the process of stellar nucleosynthesis. The power of the strong nuclear force can be seen in its role in the cores of stars, where nuclear fusion takes place. Inside stars, hydrogen atoms fuse together to form helium, releasing vast amounts of energy. This energy is what powers stars and enables them to shine. Without the strong nuclear force, nuclear fusion would not be possible, and stars would not burn. The energy released by the strong force in the form of nuclear fusion reactions is what ultimately provides the heat and light needed for life as we know it. The strong nuclear force, then, is not just important for holding protons and neutrons together in atomic nuclei, but also for the creation of the elements that make up the universe and for powering stars. Now let's turn to the weak nuclear force. Unlike the strong nuclear force, which is responsible for holding matter together, the weak nuclear force plays a very different role. It governs the process of decay and transformation within the subatomic world. This force is responsible for some of the most fundamental processes in the universe, particularly those that happen inside atoms, like radioactive decay and the fusion of hydrogen into helium in stars. The weak nuclear force is much weaker than the strong nuclear force, but it is still a crucial part of the universe's functioning. It is the force that allows certain particles, like neutrons, to transform into other particles, such as protons, in a process known as beta decay. During beta decay, a neutron inside an unstable atomic nucleus changes into a proton, and in the process, it emits an electron, called a beta particle, and an antineutrino. This transformation is essential for creating the variety of elements that make up the universe. To understand how the weak nuclear force works, it's important to recognize that it operates at an incredibly small scale, one that is smaller than the size of an atom. The weak nuclear force is mediated by force-carrying particles called W and Z bosons, which are much heavier than protons or neutrons. Because these bosons are so massive, the weak force is extremely short-ranged, acting only at distances smaller than the size of an atomic nucleus. This is one of the key reasons the weak force is much weaker than the strong nuclear force. The weak nuclear force is responsible for a wide variety of processes that occur within atoms and subatomic particles. One of the most important roles of the weak force is in the decay of unstable particles. Neutrons, for example, are not stable in isolation. When a neutron is outside of a nucleus, it will decay into a proton, emitting an electron and an antineutrino. This process is known as beta decay, and it is crucial for the creation of elements in stars and the formation of heavier elements in the universe. Without the weak nuclear force, beta decay would not be possible, and the elements necessary for life would never have been created. Another critical function of the weak nuclear force is in the process of nuclear fusion, which powers stars and provides the energy that sustains life. Inside stars, hydrogen atoms fuse together to form helium, a process known as the proton-proton chain. This process is driven by the weak nuclear force, which enables the transformation of hydrogen nuclei, protons, into helium nuclei. The weak nuclear force also plays a role in the creation of heavier elements, such as carbon, nitrogen, and oxygen in stars. While the weak nuclear force is primarily associated with particle decay and the fusion of elements in stars, its influence extends far beyond just these processes. It is responsible for many of the interactions that occur between subatomic particles, shaping the fundamental nature of the universe. For example, the weak force is crucial in the creation of neutrinos, those ghostly, almost massless particles that pass through matter without interacting with it. Neutrinos are produced in vast quantities in stars, particularly in the process of nuclear fusion, and they are some of the most abundant particles in the universe. Without the weak nuclear force, stars would not burn, and life as we know it could not exist. The weak force is also responsible for the cosmic creation of the elements, which are necessary for the formation of planets, life, and the structures that we observe in the universe. In this sense, the weak nuclear force plays a fundamental role in making the universe a place where complexity can arise, from atoms to stars, from the birth of elements to the transformation of matter. One of the most fascinating aspects of the weak nuclear force is that it only acts on certain types of particles. Specifically, it only interacts with particles that have weak charge, which is a property that is distinct from electric charge. This gives the weak force its unique ability to drive processes like beta decay, where particles are transformed from one type to another. In the early universe, the weak nuclear force played a significant role in transforming the particles that existed after the Big Bang into the matter we see today. The weak nuclear force is also responsible for CP violation, a phenomenon that allows for an imbalance between matter and antimatter in the universe. This imbalance is crucial because in the early universe, matter and antimatter should have been created in equal amounts. However, due to the weak nuclear force's actions, a slight imbalance arose, allowing matter to dominate over antimatter. This imbalance is what has allowed the universe to be made of matter, rather than having been annihilated by antimatter. In summary, the weak nuclear force plays a critical role in the transformation of matter, from beta decay to the creation of stars. While it may be weak compared to the strong nuclear force, its effects are felt on a much larger scale, helping to shape the universe and enabling life to exist as we know it. The weak nuclear force may be less obvious than the strong nuclear force, but it is just as essential for the functioning of the universe. Without it, the stars would not shine, the elements would not form, and life as we know it would be impossible. Electromagnetism, light and energy. Finally, we come to electromagnetism, the force that governs the behavior of electric charges and magnetic fields. Electromagnetism is responsible for a wide variety of phenomena, from the behavior of light to the forces that hold atoms and molecules together. In the early universe, as the electromagnetic force began to separate from the superforce, it became one of the most important forces in shaping the development of the cosmos. Electromagnetic interactions govern the formation of atoms, the behavior of electrons, and the creation of electromagnetic radiation, such as visible light, X-rays, and radio waves. Electromagnetic force is the reason we have chemistry. The electrons in atoms interact with each other through electromagnetic force, forming chemical bonds and creating molecules. Without electromagnetism, there would be no atoms, no stars, no galaxies, and no chemistry. Moreover, electromagnetism is the force responsible for the cosmic microwave background radiation, CMB, the faint glow that fills the universe and is a remnant of the Big Bang. The CMB provides a snapshot of the universe when it was just 380,000 years old and is one of the key pieces of evidence supporting the Big Bang theory. The role of symmetry breaking in the universe's evolution. Symmetry breaking is one of the most profound concepts in the universe's evolution. A pivotal moment in the early universe that laid the foundation for everything we see today, from the stars in the sky to the very atoms that make up our bodies. To truly understand its significance, we must first grasp what symmetry means in the context of physics, and why breaking it is so essential to the formation of our universe as we know it. At its core, symmetry refers to a state of perfect balance, where everything is the same in all directions or under all conditions. Imagine a perfect sphere. No matter how you turn it, it looks the same. This idealized version of symmetry was once thought to describe the universe before the Big Bang, when all forces were united in a single, symmetrical superforce. In this state, every aspect of the universe was indistinguishable from one point to another. There was no differentiation between time, space, or the forces governing matter. It was a unified, symmetric state where everything existed as one. However, when the universe began to cool and expand following the Big Bang, that symmetry was broken. This was the moment when the universe transitioned from a state of perfect balance to the asymmetric, complex cosmos we now inhabit. This is what physicists refer to as symmetry breaking. It's the moment when the forces that govern the universe began to separate from each other and take on distinct identities. Before symmetry breaking, the forces of gravity, electromagnetism, and the strong and weak nuclear forces were united into a single force. The temperatures and energies in the early universe were so high that these forces couldn't exist as separate entities. They were just different aspects of one unified force. This was true until the universe began to cool down after the initial explosion. As the universe expanded and cooled, something extraordinary happened. The forces began to separate, each developing its own unique characteristics. The cooling of the universe and the loss of energy allowed these forces to break free from the unified state they once shared. The first force to separate from the superforce was gravity. Gravity, which governs the movement of objects from the largest galaxies to the smallest particles, became distinct, and space-time began to curve around massive objects like stars and planets. Gravity's role was set. Its job would be to govern the large-scale structure of the universe, binding matter together and forming the galaxies, stars, and planets that would come later. As gravity separated, the strong nuclear force emerged, which is the force responsible for holding atoms together. This force, while incredibly powerful, operates only at very short ranges, inside atomic nuclei. It holds protons and neutrons together, preventing them from flying apart due to the electromagnetic force, which makes like charges repel each other. Without the strong nuclear force, atoms could not exist, and the structure of matter as we know it would never have formed. The next force to separate was the weak nuclear force, which is responsible for the radioactive decay of certain particles and the processes that power stars. The weak force governs the transformation of one type of particle into another, such as turning a neutron into a proton. It also plays a key role in the process of nuclear fusion that powers stars. Finally, electromagnetism, the force responsible for light, electricity, and magnetism, became distinct from the other forces. Electromagnetic forces govern the behavior of charged particles and enable the formation of atoms and molecules, which are the building blocks of all matter. This gradual separation of the forces is what we call symmetry breaking. But why is this process so significant? The answer lies in the fact that, without symmetry breaking, we would not have the complex, structured universe we see today. Symmetry breaking is what allowed the fundamental forces to take on their roles and govern the behavior of matter. Without it, the universe would remain a chaotic, undifferentiated mass of energy and particles, without the structure that allows stars to shine, galaxies to form, or life to exist. One of the key implications of symmetry breaking is the creation of mass. Before the forces separated, particles were essentially massless. They moved freely and did not interact with each other in the way we are accustomed to. But as symmetry broke down, particles began to interact with the newly emerging Higgs field, a fundamental field that permeates all of space. The interaction with this field gave particles mass, and without it, particles would remain massless, unable to form atoms, stars, or galaxies. The Higgs field allowed particles like protons, neutrons, and electrons to acquire mass, and without it, the universe would be vastly different. Particles would not clump together to form atoms, and the structures necessary for life would never have formed. Symmetry breaking also plays a crucial role in the way particles behave. In the early universe, before symmetry breaking occurred, particles were symmetrically distributed. There was no distinction between particles or their properties. Everything was uniform. But as the forces broke apart, particles began to acquire distinct properties. For instance, the strong force and the weak force, which had once been unified, began to behave differently, with different ranges and strengths. Electromagnetic forces began to operate over much larger distances, and gravity began to shape the large-scale structure of the universe. Symmetry breaking was responsible for these shifts, leading to the complex universe we now observe. However, symmetry breaking didn't just occur in the early universe, it continues to influence the universe to this day. As the universe evolved, the fundamental forces continued to shape the way matter behaves, from the formation of atoms to the creation of galaxies. On a subatomic level, symmetry breaking continues to guide the interactions between particles. In particle accelerators, scientists study the remnants of these early symmetry-breaking processes, trying to understand how they shaped the particles we see today. The discovery of the Higgs boson, for instance, provided evidence for the Higgs field and its role in giving particles mass. This was a crucial step in confirming our understanding of symmetry breaking and its effects on the universe. Moreover, the process of symmetry breaking is not just about the separation of forces. It's also about the universe's evolution over time. As the universe expanded, it underwent a series of phase transitions, much like the way water changes from a liquid to a solid as it freezes. Each of these phase transitions marked a shift in the properties of matter and the forces that govern it. For example, when the universe cooled sufficiently, quarks and gluons combined to form protons and neutrons, which then combined to form atoms. This process was driven by symmetry breaking, as the properties of particles changed in response to the changing conditions of the universe. The formation of atoms, galaxies, and stars. All of these processes were governed by the gradual unfolding of symmetry breaking. As the universe continued to evolve, so did the effects of symmetry breaking. In fact, the very structure of the universe, from the distribution of galaxies to the formation of superclusters, can be traced back to the early symmetry-breaking processes. The universe's large-scale structure, its distribution of matter, and the very way particles interact with each other are all shaped by the way symmetry was broken in the early moments of the universe's existence. The universe is a patchwork of regions that were shaped by the forces that emerged from symmetry breaking, creating the vast cosmic web we observe today. At the quantum level, symmetry breaking also helps to explain the behavior of elementary particles. The standard model of particle physics, which describes the fundamental particles and forces, relies heavily on symmetry breaking to explain why certain particles have mass, why particles interact in the way they do, and why some particles decay while others do not. Without symmetry breaking, the standard model would not make sense, and we would be left with an incomplete understanding of the universe's fundamental workings. The role of symmetry breaking is not limited to the universe's infancy. It continues to play a key role in our ongoing exploration of the cosmos. In the search for a unified theory of everything, physicists are trying to understand how all the fundamental forces might be related to one another. Some theories, such as string theory, suggests that at extremely high energies, the forces could reunite into a single superforce once again. If this is true, then the process of symmetry breaking would play a crucial role in understanding how these forces evolved and how they might one day be unified once again. Symmetry breaking also leads us to some of the deepest questions about the nature of the universe. For instance, why did the universe break its symmetry in the first place? Was it a random process, or was there some deeper reason behind it? What caused the Higgs field to emerge and give particles mass? These are questions that physicists continue to grapple with, and they represent some of the most profound mysteries of the universe. In conclusion, symmetry breaking is not just a scientific concept, it is the key to understanding the universe's evolution. It marks the transition from a perfectly symmetric, undifferentiated state to the complex, structured cosmos we observe today. From the formation of the fundamental forces to the creation of mass and the large-scale structure of the universe, symmetry breaking has shaped every aspect of our existence. It is a process that continues to influence the universe, from the behavior of elementary particles to the distribution of galaxies. As we continue to study the cosmos, symmetry breaking will remain at the heart of our quest to understand the universe's origins and its ultimate fate. The lasting legacy of the birth of forces. The birth of the fundamental forces of nature has left an indelible mark on the very structure of our universe. When we think of forces today, we usually think of gravity pulling us down, of magnetism holding objects in place, or of the strong nuclear force binding atoms together. However, the events that unfolded in the early moments of the universe, right after the Big Bang, laid the foundation for these forces and ultimately determined the course of everything that would follow. Understanding the birth of these forces is not just about comprehending how the universe began, it's about unraveling the very nature of existence itself. In the earliest moments of the universe, just fractions of a second after the Big Bang, the universe was a hot, dense soup of particles, energy, and radiation. The conditions were so extreme that the forces that govern everything from the smallest particles to the largest galaxies were all unified into a single entity, which we now call the superforce. In this state, there was no distinction between gravity, electromagnetism, and the strong and weak nuclear forces. Everything was connected, bound together by an almost unfathomable energy. But as the universe began to expand and cool, this superforce began to break apart into its constituent forces, each taking on a distinct and vital role in shaping the cosmos. The moment when these forces split apart was a crucial point in the universe's history. The cooling of the universe allowed space and time to emerge, and it was during this time that the laws of physics as we know them began to take shape. The separation of these forces wasn't just an abstract process, it was the key to the creation of matter, energy, and the universe as we experience it today. Each of the four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, became distinct and started to influence the universe in different ways. The separation of these forces, often referred to as symmetry breaking, allowed for the birth of the universe's structure and the conditions that would eventually lead to the formation of stars, galaxies, and life itself. For instance, gravity, the force that pulls objects toward one another, was the first to emerge from the superforce. Once it separated, it immediately began to shape the universe by curving the fabric of space-time itself. Gravity's influence is seen everywhere, from the way planets orbit stars to the way light bends around black holes. It is the force that holds the universe together, keeping galaxies and clusters of galaxies from flying apart. Gravity also governs the formation of large-scale structures in the universe. From the birth of stars to the collision of galaxies, gravity has been the driving force behind the evolution of the cosmos. Without gravity, there would be no stars, no planets, and no life. The electromagnetic force, which controls electric charges and magnetic fields, also separated from the superforce. It is responsible for almost all the phenomena we encounter in our daily lives, from the light we see to the electricity that powers our homes. Electromagnetism governs the interactions between charged particles and forms the basis for chemical reactions and the creation of matter. Electromagnetic interactions allow electrons to form bonds with atomic nuclei, creating the atoms and molecules that make up everything we see around us. Without electromagnetism, there would be no chemistry, no atoms, and no matter in the form we know it. Electromagnetism also plays a vital role in the way energy is transmitted across space. The speed of light, the energy that flows through our bodies, and the heat we feel from the sun are all a result of electromagnetic forces. While gravity and electromagnetism were the first forces to emerge, the strong and weak nuclear forces soon followed. The strong nuclear force, which holds the nuclei of atoms together, is responsible for binding protons and neutrons into stable atomic nuclei. It is one of the strongest forces in nature, yet it only acts at extremely small distances on the scale of atomic nuclei. The strong force is what makes matter stable. Without it, atoms wouldn't hold together, and everything would disintegrate. The weak nuclear force, on the other hand, governs the decay of particles and the process of nuclear fusion. It is responsible for processes like radioactive decay, which plays a vital role in the creation of elements and stars. The weak force is also crucial for the process of fusion that powers stars and produces the light and heat that sustain life on Earth. However, these forces didn't just emerge in isolation. They interacted with one another in ways that would set the stage for the universe's evolution. As the universe cooled, these forces started to shape the fundamental building blocks of matter. The cooling of the universe allowed quarks, gluons, and other particles to combine into protons and neutrons, the building blocks of atoms. The strong nuclear force held these particles together, while the weak nuclear force allowed for the transformations that would create new elements. Electromagnetism began to govern the interactions between particles, leading to the formation of atoms, and gravity began to pull these atoms together, forming stars, galaxies, and eventually planets. The interplay of these forces created the very structure of the universe, from the tiniest particles to the largest cosmic structures. The birth of these forces also had a profound impact on the way the universe evolved. The cooling of the universe and the emergence of distinct forces allowed for the formation of matter, the creation of atoms, and the formation of the first stars. These stars, powered by nuclear fusion, created the heavy elements needed for life. The formation of galaxies, the expansion of the universe, and the eventual development of complex structures like black holes and neutron stars were all driven by the forces that emerged in the early universe. As the universe continued to expand, the forces that had separated in the beginning remained central to the ongoing evolution of the cosmos. Gravity continued to shape the large-scale structure of the universe, forming galaxies, clusters of galaxies, and the vast cosmic web of interconnected matter. Electromagnetism remained crucial to the interactions between particles, enabling the formation of complex atoms and molecules. The strong and weak nuclear forces continued to govern the behavior of subatomic particles, enabling the creation of the elements and driving the processes of nuclear fusion in stars. Together, these forces continue to shape the universe in ways we are still trying to understand. In fact, the legacy of the birth of these forces continues to be felt today. Modern physics is still grappling with how these forces interact, and scientists are trying to unify them into a single theory that can describe all of the forces of nature in one framework. The search for a theory of everything, a unified theory that explains all of the fundamental forces, is one of the greatest challenges of modern physics. This theory would unite gravity, electromagnetism, and the strong and weak nuclear forces into a single, all-encompassing theory. It could help us answer some of the most profound questions about the nature of the universe, from the behavior of black holes to the origin of the cosmos itself. The quest to understand the birth of these forces is not just a theoretical pursuit, it has real-world implications. The forces that emerged in the early universe continue to shape everything we experience. Gravity controls the motion of planets, the orbits of moons, and the behavior of stars. Electromagnetism governs the behavior of light, electricity, and magnetism, making modern technology possible. The strong and weak nuclear forces govern the behavior of atomic nuclei and the processes that power the stars. These forces are at the heart of everything, from the chemistry of life to the structure of the cosmos. The birth of these forces was not just the beginning of the universe, it was the beginning of the conditions that allowed for life to exist. The forces that were born in the early moments of the universe made it possible for matter to form, for stars to shine, and for planets to evolve. They are the reason we have atoms, chemistry, and the very possibility of life. Without these forces, the universe would have remained a chaotic, featureless sea of radiation and energy. Instead, we live in a universe of incredible complexity, where matter and energy interact in intricate ways to create the beauty and order we see around us. As we look to the future, the legacy of the birth of the forces will continue to shape our understanding of the universe. The search for a unified theory of physics, the study of dark matter and dark energy, and the exploration of the farthest reaches of the cosmos all depend on our understanding of these fundamental forces. The birth of these forces was the first chapter in the story of the universe, and as we continue to explore the universe, we are writing the next chapters in that story. The birth of the forces was not just an event in the history of the universe. It was the key to everything. It was the moment when the universe transitioned from a state of chaos and uniformity to one of complexity and diversity. It was the moment when the very building blocks of matter were created, when the forces that govern the cosmos began to take shape, and when the conditions for life were set in motion. The legacy of this event is still with us today, and it will continue to shape the future of science and our understanding of the universe for generations to come. In the end, the birth of the fundamental forces is more than just a chapter in the history of the universe. It is the foundation of everything we know and everything we are still striving to understand. It is the story of how the universe came to be, how it became the place we call home, and how we, as sentient beings, are a part of this vast, interconnected cosmos. Where did it all come from? So, here's the million-dollar question. Where did all this energy and matter come from? It's the question that has haunted scientists, philosophers, and curious minds for centuries. One of the biggest challenges in understanding the beginning of the universe is grappling with the concept of something coming from nothing. The idea is mind-bending, almost too strange to wrap our heads around, but it's a core element of modern cosmology. The birth of our universe wasn't just about creating stars or planets, it was about the very fabric of space and time itself. And even though we've come a long way in our quest for answers, the truth is, we still don't really know where it all came from. But that doesn't mean we're without clues. Some scientists propose that the universe emerged from a quantum fluctuation, a tiny, random disturbance in a vacuum. Imagine space as a sort of empty, vast ocean, where particles appear and disappear in the blink of an eye, only to vanish again. These fluctuations are so small they can't be detected, but theoretically, if a fluctuation were big enough, it could give rise to something much larger, like the birth of the universe itself. This idea challenges our conventional understanding of nothingness. We usually think of nothing as just that, nothing. But in the quantum world, nothing is far more dynamic and unpredictable than we could ever imagine. It's not really empty at all. Instead, it's filled with the potential for everything. In this sense, the universe could have emerged from the chaotic, uncertain world of quantum mechanics, where anything is possible, even the creation of a universe from what seems like thin air. But the concept of quantum fluctuations as the origin of the universe raises just as many questions as it answers. For instance, where did this vacuum itself come from? How could this quantum nothing exist in the first place? And why, out of all the possibilities, did this fluctuation lead to the universe we now know, rather than something completely different? These are questions that scientists are still wrestling with today. In fact, we don't even have a full understanding of quantum mechanics itself. It's a field of science that's still very much in development, especially when it comes to applying it to cosmology. Then there's the theory of inflation, which adds another layer to the mystery of the universe's origin. According to this theory, the universe expanded at an incredible rate during its first moments, growing exponentially in a fraction of a second. It's like blowing up a balloon so fast that it doubles in size dozens of times before you even have a chance to blink. This rapid expansion, known as cosmic inflation, is thought to have stretched out tiny quantum fluctuations, turning them into the seeds for all the galaxies and stars we see today. The idea is fascinating. If inflation really happened, it would mean that our universe started off from an incredibly dense, almost infinitely small state, and then, in the blink of an eye, it exploded outward into the vast cosmos we observe now. But here's the catch. While inflation solves some of the big questions about the early universe, like why it looks so uniform in all directions and why the laws of physics seem to work the same everywhere, it doesn't explain why inflation happened in the first place. It simply describes the process. And even more baffling, there's a huge gap in our understanding of what came before inflation. If inflation started the universe, what sparked inflation? Was there a trigger, or did inflation occur randomly? And most importantly, what came before this infinite expansion? This is the part of cosmology where things start to get truly speculative. Some researchers think that inflation could have been just a phase in an eternal cycle of expansions and contractions, what's known as the Big Bounce theory. According to this idea, the universe might not have started from a single point. Instead, it could have been part of a never-ending process of universes being born, expanding, collapsing, and being reborn again. The Big Bounce suggests that our universe could be just the latest iteration in a long series of cosmic cycles. In this model, time itself might not have a clear beginning, and there might be no first moment, only a continuous loop of birth, death, and rebirth for the cosmos. Another theory that challenges our understanding of the universe's origins comes from the field of string theory. String theory proposes that all the particles in the universe, every quark, electron, and photon, are not point-like objects, but rather tiny, vibrating strings. These strings exist in a space with more than the familiar 3 dimensions of space and 1 dimension of time. According to string theory, there could be up to 11 dimensions, many of which are hidden from our perception. What's even more fascinating is the idea that our universe might not be the only one. String theorists speculate that the universe could have come about through the collision of higher dimensional objects known as branes. These branes could have collided in a higher dimensional space, creating the universe as we know it. In this view, the Big Bang wasn't the beginning of everything. It was just the moment our brain collided with another, creating the cosmos we observe today. And yet, even though these ideas are mind-blowing, they still don't fully address the ultimate question. Why is there something rather than nothing? It's a question that goes beyond science and dips into philosophy. Why does the universe exist at all, instead of nothingness? Some thinkers argue that the universe may have been created by a higher power or intelligence. Others believe that the existence of the universe is simply the result of random chance, a product of the fundamental laws of physics. And then there are those who think that we may never truly understand why the universe exists. Maybe, they say, the answer is beyond human comprehension, a mystery that's simply too vast for our minds to grasp. The search for the origin of the universe is, in many ways, a search for our place in the cosmos. Understanding where the universe came from helps us understand who we are and why we exist. But even with all the progress we've made in science, we're still far from knowing the complete answer. Each new theory opens up even more questions, and every discovery brings us one step closer to understanding the infinite mysteries of the cosmos. Perhaps the truth is that the answer to where it all came from is something we'll never fully understand. Or maybe we're just at the beginning of uncovering the most profound discovery in human history. One thing is for certain, though. The quest to understand the origin of the universe is one of the most fascinating journeys we can undertake. So where did it all come from? Was it a random fluctuation in a quantum void? A collision of branes in a higher dimensional space? Or was it simply the result of an eternal cycle of expansion and contraction? The truth is, we may never know for sure. But the search for answers is what keeps us looking up at the stars, trying to unlock the secrets of the universe and our place in it. The truth about the universe's origins is elusive. Every answer we've found only leads to more questions. As we explore deeper into the cosmic past, the idea of nothingness before the Big Bang becomes harder to grasp. Imagine a time where not even time existed. No stars, no planets, not even the space between them, just an infinite, dense point that held the entirety of the universe. It's impossible to picture, and yet it's the foundation of our reality. When we look at the Big Bang, the moment that marked the universe's birth, we often think of it as a sudden explosion, a singular, chaotic event that sent everything flying outward. But that's only the beginning of the story. What really happened in those first few moments is far stranger and much harder to comprehend. At the very start, when the universe was no bigger than a single point, there was no room for conventional physics to operate. The forces we take for granted, gravity, electromagnetism, hadn't even formed yet. Instead, all of reality existed as a singular, almost incomprehensible point of energy. Picture the smallest, most minuscule speck of matter, one so small that it would make even the most microscopic things we know look like giants. Inside this tiny point, the entire universe sat, waiting for something to happen. But what was that something? How did this point of energy give birth to everything around us? It's in these moments that things get mind-bending. One of the most perplexing ideas that emerges from studying the origins of the universe is the concept of inflation. The idea, which was first proposed by physicist Alan Guth in the 1980s, suggests that just fractions of a second after the Big Bang, the universe underwent a mind-blowing period of expansion, growing exponentially, beyond comprehension. Imagine taking a balloon and inflating it so fast that in the blink of an eye it's the size of a football field, or bigger. This period of inflation didn't just change the size of the universe, it fundamentally changed everything we know about how the universe functions. The energy that began the process stretched out like a rubber band, creating a foundation for everything to come. It's during this brief yet incredible moment that the seeds of galaxies, stars, and all matter were planted. But while this idea of inflation helps explain the uniformity we see in the universe today, how the temperature is remarkably consistent across vast stretches of space, it also raises the question of what triggered this expansion in the first place. We still don't know. Why did it stop? What stopped it? Was there something else that ignited this inflationary explosion? And here's the most mind-bending thought. Some scientists suggest that inflation could still be happening. Not in our universe, but elsewhere. According to some theories, there could be multiple universes, each going through its own version of inflation. These bubble universes are an intriguing concept, suggesting that our universe could just be one in a series of infinite others. Think about that for a moment. An endless number of universes, each one born in its own version of the Big Bang. A multiverse. The implications of this are enormous. If we really are just one bubble in an eternal cosmic sea, then the very fabric of reality, everything we know about time, space, and existence, could be only one small part of something far larger and far more complex than we can even begin to imagine. But there's more. As the universe grew, it started to cool. And as it cooled, the forces that would eventually govern the universe began to take shape. In the first few moments after the Big Bang, gravity, electromagnetism, and the strong and weak nuclear forces were still unified into a single force. The universe was a chaotic, high-energy mess, where everything was connected in a way that doesn't make sense to us today. Imagine, for a second, a world where everything around you was the same. No division, no separation, nothing had its own identity. Everything merged into one. That's what the universe was like before the forces split apart. But as the universe cooled, these forces began to lose their unity. Gravity separated first, then electromagnetism, and finally, the strong and weak nuclear forces began to evolve into their separate forms. This splitting didn't just define the universe in a physical way. It laid the foundation for how everything works, from the tiniest particles to the most massive stars. One of the most intriguing moments in this process of separation was the birth of mass. Before this point, everything in the universe existed as pure energy. But at a certain moment, the universe began to cool enough for particles to gain mass, thanks to the Higgs field. You've probably heard of the Higgs boson, the particle that helped confirm this theory, but what you may not know is how important this field was. Without it, particles would never have mass. They'd be like light, moving freely through the universe, unable to interact with one another. No mass means no matter. No matter means no stars, no planets, no life. The Higgs field is the reason we have everything, from the stars in the sky to the atoms that make up our bodies. But as we dig deeper into the origins of the universe, the questions only multiply. Where did all this energy come from? Where did the very first particles arise? Scientists have many theories, but none of them can be definitively proven. Some say that the universe came from nothing, a spontaneous fluctuation in a quantum vacuum. This idea, known as quantum mechanics, suggests that particles can pop in and out of existence, even in a vacuum, without any apparent cause. So, is the entire universe just a random fluctuation of energy in a vast quantum field? It's hard to accept, but it's one of the most widely discussed ideas among physicists. Then, there's the theory of the Big Bounce. Instead of starting with a single point of energy that explodes outward, the Big Bounce suggests that the universe may have gone through cycles of expansion and contraction. Imagine an endless series of universes, each one born from the collapse of the previous one. Each universe is like a pulse, expanding outward, then contracting again before collapsing into another Big Bang. If this theory is true, then the universe you see today is just the latest phase in a long cycle that's been going on forever. We may have no idea how many cycles there have been, but each one sets the stage for the next. Now think about this. What if everything we understand about the universe is incomplete? Could there be dimensions or forces at play that we've never even imagined? Some theories suggest that the universe might be made up of tiny, vibrating strings in a higher dimensional space, an idea known as string theory. In this view, everything you see around you is just one part of a much larger, multi-dimensional universe. The space we experience, the space you see and touch, could just be a tiny slice of reality. Higher dimensions could exist beyond our perception, shaping the universe in ways we'll never fully understand. And what if the Big Bang wasn't a true beginning, but just one moment in the timeline of the multiverse, where universes form, grow, and eventually fade away, only to be reborn again? This brings us to one of the most profound mysteries in cosmology, the nature of time itself. Before the Big Bang, there was no time, no beginning, no end. Time, as we understand it, only began with the birth of the universe. But if time only began after the Big Bang, what happened before? Did time even exist? Some scientists argue that time itself is part of the fabric of the universe, and without the universe, there was no before. This idea is mind-blowing because it challenges everything we understand about existence. If time didn't exist before the Big Bang, then how can we even begin to understand what happened? The truth is, we can't. We're still piecing together the story of the universe's origins, and there's so much we don't understand. But here's the thing. Every new discovery we make opens a new door, a new way of looking at the cosmos. We may not have all the answers yet, but the search for them has only just begun. What we do know is that the universe, in all its complexity and mystery, is far more incredible than anything we could have imagined. And no matter how much we learn, there will always be more to uncover. The universe is still expanding, still evolving, and still full of secrets waiting to be discovered. The origins of the universe are wrapped in such a profound mystery that even after centuries of human exploration, we still can't say with complete certainty how it all began. What we do know is that the answers to these questions go beyond the realm of science and tap into something even deeper, our very existence. The journey to understanding where the universe came from is a tale that not only deals with the birth of everything we know, but also with the discovery of what it means to exist at all. We've spent thousands of years trying to explain why there is something instead of nothing, and yet, with each new discovery, we realize how much more there is to understand. Looking back, our first theories were based on myths and religious explanations. Cultures across the world offered various origin stories, most of which centered around gods or divine acts creating the cosmos. While these stories provided comfort and a sense of understanding to ancient civilizations, they never had the scientific evidence to back them up. It wasn't until the rise of modern science, particularly physics and astronomy, that we began to piece together the puzzle of the universe's origin. It all started with the idea that the universe had a beginning, a singular event from which everything we know today emerged. This idea took shape through the Big Bang theory, which proposes that about 13.8 billion years ago, the universe began as a singularity, a point of infinite density and temperature. From this point, the universe rapidly expanded, stretching and cooling over time, leading to the vast cosmos we observe today. This moment in time marked the beginning of space, time, and all the fundamental forces of nature that govern how everything behaves. Yet, as we delve deeper into understanding this process, we realize that the Big Bang itself is far from simple. While it explains the expansion of the universe, it doesn't answer the most fundamental questions. What caused the Big Bang? Why did the universe come into existence? Where did the energy and matter that started everything come from? These are the questions that physicists and cosmologists have been trying to answer for decades, but so far, we've only been able to scratch the surface. One of the most important insights came from quantum mechanics, the theory that governs the behavior of particles at the smallest scales. In the realm of quantum physics, nothing is certain. Instead of precise measurements, we deal with probabilities, and the very act of observing something can alter its state. This idea completely shattered our classical understanding of the universe, where everything had to fit into neat and predictable patterns. In the quantum world, everything is unpredictable, chaotic, and in a constant state of flux. This is the same environment that existed at the dawn of the universe, an unstable, unpredictable quantum foam, where the very fabric of reality itself was in the process of being created. This leads to the concept of inflation, which proposes that in the earliest moments of the universe, it underwent an incredibly rapid expansion, far faster than anything we can comprehend. During this period of inflation, the universe grew exponentially, from something smaller than a proton to the vast expanse we know today in just a fraction of a second. This rapid expansion is what explains the uniformity of the universe we see now. It also helped explain some of the strange aspects of the universe that defied conventional theories, such as the flatness problem and the horizon problem. However, this inflationary model, while groundbreaking, left us with even more questions. If inflation caused the universe to expand so rapidly, what triggered it? Why did it stop? Some theories suggest that inflation continues in some parts of the universe, while creating a vast multiverse where different universes are constantly popping in and out of existence, each with its own set of physical laws. Others suggest that the universe we live in could be part of a never-ending cycle of expansion and contraction, known as the Big Bounce. But even the most popular theories still don't fully explain where everything came from. Could the universe have been created from nothing? Some physicists propose that our universe could have emerged from a quantum fluctuation in a vacuum, essentially a random blip in the fabric of reality. Others believe that our universe was the result of the collision of higher dimensional spaces, as suggested by string theory. According to string theory, the universe is made up of tiny, vibrating strings that exist in a multidimensional space far beyond our usual understanding. These strings could have collided and created the universe we know today. At the heart of the mystery is the question of why there's something instead of nothing. Many physicists believe that the universe is a product of natural laws and random processes without any underlying purpose or design. Others, however, believe that the universe's existence points to something more profound, a deeper meaning or force that we have yet to fully understand. Is the universe the result of a series of random events, or is there a greater purpose behind its creation? The more we learn about the origins of the universe, the more we realize how much we don't know. Every new discovery raises more questions, and every answer seems to open up even deeper mysteries. As we look further into the cosmos, we see galaxies colliding, black holes devouring stars, and cosmic events that stretch our imagination. Yet, in the grand scheme of things, these events are just tiny pieces of the puzzle. Small clues that might one day help us understand the true nature of our universe's birth. We've come a long way since our ancestors first looked up at the stars and wondered about the origins of the universe. From the first rudimentary telescopes to the most advanced space observatories, our understanding has grown exponentially. But even with all the technology and knowledge at our disposal, the mystery of the universe's birth remains as elusive as ever. Perhaps the biggest lesson we've learned from this journey is that the universe is far more complex and awe-inspiring than we ever imagined. It's not just a collection of stars and galaxies. It's a vast, interconnected web of forces, particles, and dimensions that stretches across time and space. And as we continue to explore the cosmos, we will undoubtedly uncover even more about our origins. Discoveries that will challenge our understanding of reality and force us to question everything we thought we knew. In the end, the story of the universe's birth isn't just about the beginning of everything we see around us. It's about our place in the cosmos, our connection to the stars, and the mysteries that bind us all together. As we continue to search for answers, we may never fully understand the true origins of the universe. But that doesn't mean the journey isn't worth it. After all, the pursuit of knowledge is what makes us human, and the questions we ask today will shape the discoveries of tomorrow. So while the answer to how the universe began may still be out of reach, one thing is certain: we're closer than ever to understanding our place in the vast expanse of space and time. And that journey, in itself, is worth more than any answer we could ever find. If this journey through the universe's origins blew your mind, don't stop here. Hit that subscribe button and dive deeper into the mysteries of space with our next video.